Hello friends, welcome to our channel CSE GURUS. Myself Shravan Kumar, Manthri technical trainer. In this series of video lectures, we'll see the concept of data structures, that is top 90 data structure MCQs. Yeah, you can watch my previous videos like top 100 CMCQs and next 50 CMCQs. You can Google it and you can find these things in my channel. So here the MCQs consist of the data structures, which is of, I told you, easy, medium and hard, and mainly for the students who are preparing for placements and techies who want to get the thorough knowledge in data structures. We'll start now. Yeah, going to the first question: what is the infix version of the following postfix expression? One thing I want to highlight here: when you see the question, first try to answer it. Just make the video pass, then you try to answer. Afterwards you can see the answer. So going to this question, so infix version is you have to find, and this is a postfix expression is given. Basically we know that what is infix, what is postfix, what is of course prefix also. What is infix? Operator in between operands on left and right side. Okay, and if I say what is prefix, prefix means pre, that means operator first followed by operands. That means this plus operation will be done for two operands. Now what is postfix? Of course this is given here. So operator at the last. So something like AB plus means, if I want to convert this AB plus into infix means, which will be A plus B, right? So here also the question is asking, this is postfix, how to convert it into infix. So we'll try to solve. Very simple. Of course you can go for tree like manner, everything operator in between operands you can write. You can construct the like tree like structure. Okay, so instead of that, directly you can follow like, yeah, going to the right like this until operator comes. So whenever operator gets, you stop there. So now here is the operator, so I'll stop and I'll take only previous two variables or operands. So here what are those two? 12 and x. So x 12 plus, so if AB plus I can write it as infix means A plus B, right? So like this. So x 12 plus means, which I can write it as x plus 12, right? So this x plus 12 I have to write first. Okay, yeah, I'll take here x plus 12 first, then I'll take this entire part, whichever is converted. I'll take this entire part which is converted as something, a variable A. Okay, now AZ is one operand, Z is one operand, right? So now AZ, Z followed by 17, it's not an operator, so continue, Y not an operator, continue, plus, now it is an operator. So plus is an operator you have to take, and now you take previous two operands, okay, Y and 17. So 17 Y will become, that is plus, will become 17 plus Y, right? So 17 plus Y, which this part is completed, right? So this I'll take it as B. Now if you want, you can take something like A Z B 42 star slash plus. Now imagine this is your expression, like x12 plus means something like, if I give x value, this entire I'll first evaluate. So something, the value, some constant value you will get it, right? So that constant value I have taken it as something like A. So now I'll check it out like this. 42 is over, then star, it's an operator. Now previous two operands, you can see 42 by previous, this is entirely evaluated. Okay, now you can take this one star for what? B and 42, only two, right? B, what is B? This 17 plus 5. So for this 17 plus 5 I have to go for 42 with multiplication. Okay, but now you have to check it out clearly, like into and plus. So which is which you have to do. Actually if I keep like this, what happens? That means Y into 42 will be calculated first, right? According to the operator precedence priority, but which we have to calculate it according to the postfix, that is 17 plus 5 has to be calculated. That's why I'll give here a priority by taking a braces. Okay, now if I write 17 plus y into 42 means 17 plus y will be calculated first. So now this entire part is calculated. Let it be this entire part. I'll take something like you can take B or whatever it may be. I'll take C. So now I'll write this one. Okay, A Z C slash plus. Now you can take ZC slash, right? After C, what is the next you are getting operator slash. So to be applied to Z and C. So what is Z here? Z is as it is, slash the division by C. So what is C? Entire this part, right? So now I'll write here Z slash 17 plus y plus into 42 this entire part division, right? I have to give this priority. Why? Because division is the first priority if you go with the left to right, right? Even multiplication and division are both same priority, but division will come first. Why? Because that is according to the associativity, right? So according to the associativity, left to right is there for multiplication and division. So that's why, in order to avoid that, first I'll give the priority for this one. So now the part is everything is over and except this one plus is there, and left part you have A Z slash. This entire part is completed, right? So this entire part is completed. This part I'll take it as something like D. Now plus is there. So AD plus, I have to write it as A plus D. Now what is A? X plus 12, right? Now Z I have to write with plus Z divided by, this is the entire, right? 17 plus y into 42, right? Now you cannot make like x plus 12 plus z over whole brace. It's not like this, right? So z divided by this has to be done, then only this part has to be taken, right? So like this. Anyway, if you are getting confused, for every operation you have done, you can keep braces, so where you won't get any confusion. Okay, now you can think of this one, what this answer. Okay, so is this correct? No. Why? Because this is, you can see, x plus 12 plus z by, this part has to be completed, then only this separate has to be done. It's not like x plus 12 plus z combinedly divided by, it's not like this. So this part is not, this is feels like same, but you can say there are braces missing. In this case, what happens here? Y into 42 will be done first, but here 17 plus y has to be done. This is not correct. Okay, and you can take this one, if this part, okay, if I take this part, what happens? 17 plus y, this is fine, into 42 is fine, but if you don't give this braces, what happens? Z divided by 17 plus y, this part will be calculated, then into 42 will be calculated. This is also a wrong one, right? So I told you why I have to give the braces. So this part will be calculated, so this is a wrong. Now you can see this part. So according to our answer, 17 plus y into 42, this entire part, and z divided by this entire part. Of course x plus 12 will be calculated anyway first, so then addition of this part, this whole part and this part has to be done actually, right? So this is about the infix to, postfix to infix expression. The answer is D. So option D is the correct answer. Going to the sorting technique, the MCQ on sorting. A sorting algorithm that traverses through a list, comparing adjacent elements and switching them under a certain condition. So what is this? Where we can find adjacent swapping. So is it an insertion sort? It's not. So in insertion sort, every element, okay, will be inserted according to the position. We'll compare from that position. It's not like every time adjacent. And next, heap sort, of course it's not, it follows the concept of tree, like binary tree. And quick sort, which follows according to the pivot element, not every time adjacent. So bubble sort, yes, which is always an adjacent. Okay, so always adjacent swapping. Like let us suppose if I take some elements like 20, 10, 50, 40, 30. So the comparison will be like this: 20 is compared with 10. Let us suppose if it is increasing order, this will be swapped. Here 10, here 20. 20 and 50, yes, they are in order. 50 and 40, no. 40, 50, 50 and 30, no. So 30, 50. So like this, which will happen every time adjacent swapping. So this is what we called as bubble sort concept. So the answer is option D. And you can see my my channel where I uploaded all sorting techniques, all sorting techniques with clear expression. Not only these four: selection sort, bubble sort, insertion sort, med sort, quick sort, heap sort, counting sort, radix sort, bucket sort. Okay, like this, all those sorting techniques I made it as a video and series of videos, and you can watch in my channel. You can find a playlist for that. So here the option is D. So complexity of bubble sort. Just now we have seen what is bubble sort. The complexity of bubble sort in best case. So what is in best case? So let us suppose in bubble sort, in general, the complexity we take it as n square, right? So we'll take n square. Why? Because we'll use two nested for loop. That means adjacent swapping will be done. Okay, like if I take 20, 10, 30, 50, 40. So adjacent swapping every time, and what is the largest element will go to the last. Okay, next I need to come again, what is the next to largest, like this in every iterations, number of iteration. Something I'll write like this so that you may not confuse. Like this, next in you will find this one, next you will find, next you will find, like this. Now we have to say what is the best case, what is the worst case, and average case. So in general, this is the worst case we can take every time. Okay, every time we will get the element at starting. That means if it is in decreasing order, we have to find an increasing order. Every time it has to swap every time. That is a worst case. Anyway, we'll get n square. So what is the best case? What is the best case means, if let us suppose all the elements are given in order only. Let us suppose I have given the elements like this. So now I want to sort them. So let us suppose if I want to sort them. If I give in general bubble sort, it will go for, of course, n square complexity. But we can write a code where it will go for only n, which is n only. So how it is means, we'll just check it out in the first pass. I'll check it out first and second element is that 10 is greater than 20. That means if it is greater, then only we have to swap, right? So 10 is less than greater than 20, no. 20 is greater than 30, no. 30 is greater than 40, no. 40 is now in one pass. If I don't get any swapping, then no need to go for next iteration. That means in the one pass itself, I'll get the answer. So that means instead of n into n, I'll go for n into 1, right? So one for loop for checking the adjacency. If no adjacency happens, then no need to go for that. So some if condition we'll write, then directly we will get this sort of the flexibility you can find for our bubble sort only, bubble sort cases. So that is why even for another also you can check it out here. That's why we can get the best case in n only. So the answer is option A. Of course, if you want this entire program, you can watch in my channel. So that entire program clearly, even how it is best case with program and execution, I explain. Okay, you can find that bubble sort in sorting techniques. So there you can clearly see how it is theta of n. Very important question. This is for placements point of view. Moving on to the next one. If the given input array is sorted or nearly sorted, which of the following algorithm gives the best performance? So we have taken the previous example of bubble sort in case where already sorted elements, then bubble sort is giving best case like theta of n, like this it is. But is there any answer as bubble sort here? No. Then what we have to do? Check it out with another alternative. So if I take with med sort, what happens med sort? So whatever it may be the elements, it has to divide it into equal parts, right? So it has to divide, even if it is sorted order also it has to divide. So that's why that is a complexity n log n for this one. This is not quick sort. Will it give the best? No. Even in best case also it goes to the n log n almost, right? In case of worst case it is going to the n square. So where the elements are given in sorted order, which gives the worst case complexity. Remember this point. Of course, in best case, if the elements are given in sorted order, bubble sort gives the best, but whereas quick sort gives the worst. Selection sort, whatever it may be the elements, it has to check for minimum every time, and swapping with the first element, right? Every time the element with unsorted and sorted list. So whatever the minimum element, every time, every pass you have to check it out, and you have to swap with the first element in the unsorted sublist. Here also not, it has to take and square whatever it may be the elements. So of course you can say this one is a correct answer, insertion sort. Why? Because here inserting an element, if you give the all elements in sorted order, every element is at its position, right position. Is there any need to swap anywhere? No. That part has to be checked in one pass. Okay, you have to take the last element, check it out for this every time taking every element, what is its position, check with the first next neighbor element. If it is not swapping, then leave it like this every time. That means what happens in bubble sort, it is n into 1, but whereas in insertion sort it is 1 into n, right? So for n elements, each time it goes only one time. That means one time iteration only you will find for each element, because it won't swap every time. Let us take 10, 20, 30, 40, 50 will take. So let us suppose if I equals to 1, we have to start in insertion sort. 20 checking with 10, not swapping, going to the next pass. 30 with 20, no. 40 with 30, no. 50 with 40, no. That's it, over. So every iteration it goes only one time into n elements. So this is about insertion sort, and I told you clear programs you can see there itself in my channel, and you can find the videos for each one. Now the answer is option A. So bubble sort and insertion sort will give the best performance when all the elements are given in sorted order, whereas quick sort gives the worst case performance. Remember this point. Now the question is from binary search tree. I hope you know the basic of binary search tree, whereas it is a tree where it finds left and right element, and like this. And not only that, left subtree is always the elements are less than the root, and right always are greater than the root. Anyway, I'll show you with example. While inserting the elements, what it is asking, the element at the lowest level. So first I'll explain what is this binary search tree by inserting these elements in a empty binary search tree. Okay, so first element 71 I'll insert in the empty binary search tree as a root node, right? Now the 65 next element. So I have to check with 71. It's not like you have to insert at the left, you have to check it out. 65 is less than 71 or greater. If it is less than, left. If it is greater than, right side. So 65 is less than, so left side. Now 84 is greater than, right, for 71, so 84. Now 69, so 69 is less than 75, come to the left, but it is not empty. Check it out for this one. 69 is less than 65, no, greater than, so right of 69. Now 67, so it is less than 71, come to the left, greater than 65, come to the right, less than 69, come to the left of this one. Now 83 greater than 71, come to the right, less than 84, come to the left. That's it, right? So like this we need to do, and you can conclude the left subtree of 71 or less than, right subtree are always greater than. You can see 84, 83. And not only for this, every node 65, right side 69 and 67 greater, left side nothing is there anyway. For 84, left is 83, right? So like this it is there, and what it is asking, the element at the lowest level. So answer is option B. What is there in the lowest level? 67. And remember, only at most two children for binary search tree we know, right? So answer is option B, that is 67 at the lowest level. Moving on to the question number 6. So which is with respect to the concept of stack. There are 5 items A, B, C, D, E, and are pushed into the stack one after the other starting from A. Okay, then stack is pop 4 items and each element is inserted in a queue. Okay, so this is a concept regarding stack and queue. I think you know very well about stack and queues, the basic concepts of stack. So where in stack you can insert from only one end. Okay, you can push, we call it as, and when you delete you call it as pop. Whereas in queue, so whichever is the element first inserted will be deleted first. So I can say here you can insert from rear and I can delete from front, right? This is, you can push and pop. Okay, yeah, we'll see here A, B, C, D, E are pushed into the stack one after the other. So if I move here, it is a stack, right? So this is a stack. So A, B, C, D, E. Now after pushing each and every element, you can see now after 5 elements the top of the stack is E, right? So the top of the stack is E. Now if I pop, the element E will be deleted from the stack, right? So this is what, and it is asking after inserting the stack is popped 4 items and each element is inserted into a queue. See here 4 elements, that means you cannot take like B, C, D. So from top, so E will be taken first, which will be taken into Q, then D, then C, then B. Only 4 elements it is, right? So 4 elements inserted here. E will be inserted, then followed by D, like this. So that means what happens here, E, then D, then C, then B will be inserted into a queue. The 2 elements are deleted from the queue. Now what are the elements I have to delete from the front, right? So E and D will be deleted. Okay, now and pushed back on the stack. So here if you see the stack, after deleting all these 4, now you have A only. So here after A, now E and D, see it is E and D, whichever is inserted first will be deleted. That's why E will come first, then D will come, right? So pushed back onto the stack. Now one item is popped from the stack. What is that? So now you can see this is a stack. What is the top element from the stack? D, which will be popped. So this is a question given like to know the difference exactly, like what happens when you go for stack and queue, how you need to insert and delete. So finally the popped item is our D, right? So option D is our correct answer. So the item is D. Coming to question number 7. A binary search tree, again BST question, is generated by inserting in order of the following integers. So these integers are inserted into a binary search tree. The number of nodes in the left subtree and right subtree are respectively. So the question is asking how many elements are there in the left subtree, how many elements are in the right subtree. Actually the answer you can get directly without constructing the binary search tree. Okay, anyway I'll let you know. Before that, first I'll construct. Okay, construct the binary tree 50. According to the rules I'll construct 50, then check it out 15, it is less than, that's why left part, then 62 starting from 50, so greater here. Next 5 is less than 50, yes. 5 is less than 15, yes. So here next 20 is less than, okay, 15, yes, but for 15 it is greater. Next 58. So like this we need to construct. Now you can see like this you need to construct the binary search tree one by one, checking at every point whether it is greater or lesser. If it is lesser, go to the left part. If it is greater, go to the right part. Like this for every node until you will get a leaf. Then you have to add those elements. Now you can see how many are there in the left part of the root. Root is 50. The left part you can see 1 2 3 4 5 6 7 on the left part, and right part 1 2 3 4. So answer is option B. So without constructing this also you can get like. So first we have to take the first node, which is a root. Check it out for how many are less than 50. So that is the left number of nodes, that is on the nodes in the left subtree. How many are greater than, that will be right part. You can observe here. So less than 50, how many are there? 15, 5, 20, 3, 8, 37 and 24. How many? 7. And greater than 50, 62, 58, 91. 4 elements, of course. 60 is also there. So 4 elements. So that's why directly you can get the answer for like these questions. Of course this part is not required. Anyway, one more thing, if you observe in binary search tree, when you construct the leftmost, extreme leftmost node, which is the smallest of all the elements, rightmost node, which will be always largest element in the binary search tree. Of course this part also you remember. So in this question the answer is option B. Coming to this question number 8. While searching for the key value 60 in a binary search tree, so we have these nodes, these values are traversed. Okay, of course these after traversing 10, 20, 40, 50, 70, 80, 90 are traversed, not necessarily in the order given. This is not the exact order it is given. How many different orders are possible in which these key values can occur on the search path from the root to the node containing the value 60? So it is telling like whenever you are searching in a binary search tree, I think how to construct a binary search tree we have seen in the previous question. But when you want to search a binary value, okay, when you want to search for a binary value, so in between you find some nodes. What are those nodes? 10, 20, 50. Not necessarily in this order. It might be another order. Might be you find like 50 followed by 20 followed by, might be 10 followed by 70. Like this. The order it is not given, but we have to find how many different orders are possible. In general, if you ask me, I'll say one thing is, one simple one is like this. After 40, okay, there is no 30. So I'll write why, because for 10 the node which is 20 is greater, that's why right side. 40 is greater. Next 50 always should come on the right. But can I get 60 directly? If I write directly 60 here, our answer is over, but I need to find these 3 elements are also in between. So where these 3 elements should be? After 50 I need to get 60 here, but if I write 60, these 70, 80, 90 also should be there. How these 70, 80, 90 should be? So those elements are also should be. I cannot write 70 here, but if I write 70, what happens? Then if I write 70 here, what happens? 60 should come here, but if I take 80, it will go there. So that's why. So these 3, whatever the values less than 60 should be in ascending order. Whatever are greater should be in descending order. You can see, instead of taking 70, I'll take 90. Then I'll take 80. Then I'll take 70. Now I'll take 60. Now you can see, let us suppose if I want to insert 60, will it follow the same? You can see 60 means it is greater than 10. It will come on the right side. It is greater than 20. Yes. It is greater than 50. Yes. It will come there. 90. It is greater than 90. No. Comes to the left. 80. Again left. Again left. Now 60 will come here. Right? So like this we need to check it out. Or is this one arrangement? Yes. Another arrangements are also there. Like I'll take 10. Somewhere 90 I'll write. Okay. Somewhere 20 I'll write here. Okay. That means which we need to follow that, right? So like this we need to get. That means your 10, 20, 40, 50, all these 4 elements always should come in the ascending order. It should not be like 20 then 10. If I write like this, where 60 will go? Here it will go. So that means it is not following the path. That means when you start 20, you are missing 10. So that is what. So that's why 10, that means these values which are less than should come in the proper order, that means in the increasing, whereas the values greater than should come in the descending order. So now if I write like this, first I'll take 10, 20, 30, 40, 10, 20, 40, 50. These four elements, these four elements should always come in ascending order. Out of how many positions? How many totally? 7 positions, right? So total 7 positions. 1, 2, 3, 4, 5, 6, 7. Total 7 positions. These 4 I can arrange. How many ways I can arrange? 7C4 I can arrange. Like 10 can come here, or here, here, or here. It can't come here, right? Why? Because if 10 comes here, 20, 40, 50, 3 cannot be arranged in 2 blank spaces, 2 spaces. So that's why 4 ways. And for 20 also, 1, 2, 3, 4 ways. For 2 elements next, 40 also, 1, 2, 3, 4 ways, 50 also. So this can be arranged in 7C4 ways. And once we arrange 7C4 ways, what about 90, 80, 70? Will it be arranged in 7C3? No. Why? Because once we arrange these 3, there is only one option always for 90, 80, 70. Why? Because only 3 fill-ups are there, and these 3 it has to be filled. Like let us suppose 10 here, 20 here, something 40 here, 50 here. See, you must keep 90 here only. You cannot keep here. You must keep 90 here only, 80 here only, 70 here only. There is no like 80 here and 70, 90 here. You cannot keep, right? So this always must be in 1. So 7C4 into 1, which is we have to find, which you find the answer is 35. So our option A is correct answer. So we need to be careful for like these questions. And if you want further explanation, clearly theoretically you can check it out, this one. You can clearly read it, you will find the answers. 2 types of explanations are given here. Yeah. Question number 9. Which of the following is not required for binary search algorithm? It's not about binary search, it is only binary search. We know that binary search always search for the middle element. If not, it divides into 2 parts, right? Left part and right part, like this it will go, we know that. And so which is not required condition? So we'll see. So first option, the list must be sorted. Yes, this is the definite condition. This must be required actually, right? So when you go for binary search, the element must be in sorted order, of course, whereas in linear search, which is optional, there should be direct access to the middle element in any sublist. Yes, why? Because the method follows like always, it has to find what is the middle value, it has to check if it is equal, directly returns, otherwise it will check for the left part or right part, like this. And there must be a mechanism to delete or insert the elements. So we hope like we never insert and delete the elements when you go for binary search, we just traverse. So that's why, so this option is not required actually. And of course, if you see number of values should only be present, that means number values only should present in a binary search tree. Of course, true, very true. But what if I give a alphabets A, C, B, something like D, something like X? So in this case also we can take them by taking the ASCII values, right? ASCII values for this is 65, this is 67, like this is 66. So we can take, again it is a numbered value, right? So this is also required. So that's why our option C is the correct answer. For this one it is asking which is not the required condition. So option C is the correct answer. The result of evaluating the postfix expression. So 5, 4, 6, then it is given, and I explained about what is infix, prefix and postfix in my previous questions. Now you can see here how to go for this one. Simply follow these operands values, okay, then immediately when you get operator, so immediately evaluate the expression. So 4 6 plus, which is equals to 4 plus 6, which is 10. So here it will be 5 followed by 10 * 493 hash plus star. So now after this 10 star is there again operator previous to 510, which is 50, then 493 hash plus star. So where is again from operator from left to right? So here it is division. So 9 divided by 3. I'll write this as it is, 9 divided by 3, which is 3. Here plus, here asterisk, and plus, now you can see 4 plus 3, which is 7. Here 50, here star. So 50 into 7, which is 350, right? So like this. Of course, the advantage compared to infix notation, the advantage of postfix over infix is, so here there is no need of like operator precedence like this. We are not yet confused, right? So in infix, if I say 5 plus 4 into 10, so which has to be done first? Actually 4 into 10. So like this we need to check it out. So here the answer is option B. Moving on to the next one, question number 11. The following postfix expression with single digit operands is evaluated using stack. So this expression we are evaluating using stack. So the question is asking is, of course, cap is the exponential operator. What are the top 2 elements of the stack after the first asterisk is evaluated? So there are 2 asterisks to be evaluated, but we want the answer when this position comes. What are the top 2 elements, of course, in the stack, right? So I'll take a stack here. How the operations will come, we'll see. Like this it will be initially. So whenever there is an operand comes, I'll push into the stack. Whenever there is an operator, now I have to pop 2 elements, then I have to operate, right? So first the element 8, I'll push into the stack. Next again operand, yes, push into the stack. Next 3, push into the stack. Next cap, of course the operator. Now I have to pop 2 elements. So 3 2, okay, yeah, of course it has to be taken. So the element 3, then I have to take 2, and now we need to have cap operation. So like this it will be, it's not 3 cap 2, it is 2 cap 3. So like this it will be. And what is 2 power 3, which is 8. So now this operation, the value is 8. Now 8 has to be pushed, right? So these 2 has to be deleted, and now I'm pushing 8. Now what is the next operand? That you are getting operator, right? So slash. So whenever there is an operator, I have to pop the top 2 elements. What are the top 2? Anyway, 2 elements are there. 8 and 8, 8 divided by 8, which is 1. So I have to remove these 2, and 1 will be pushed onto the stack. Now 2 comes. So when 2 comes, I'll push into the stack. 3, I'll push into the stack. Now asterisk. Now I have to pop the elements. Okay. So now if I pop, 3 and 2 should be popped. That is like this asterisk. So which is 6. Now 6 has to be pushed here. Now this is a question it is asking the top 2 elements of the stack after the first asterisk is evaluated. I evaluated. Now the elements are 6 and 1. Option A. And here we need to remember this point. Whenever you pop 2 and 3, if you write 3 comma 2, it will be like 3 square. So remember carefully which value, which operand to be taken first. So that's why I have given this question. In order to avoid the confusion, you have to ensure this one, right? If you write 3 square, your answer will be wrong, right? Coming to question number 12. Convert the following infix expression into equivalent postfix. Converting infix to postfix, I think it is little bit easy compared to the other conversions like postfix to infix. So this is simple, like how we'll do with respect to the expression evaluation. So simply I'll start with A plus B is there. I cannot directly convert. I'll check it out which is the first priority. B cap D. Cap in the sense here exponential. Now if I compare plus and exponential, why? Because it is in the braces, right? So only two operators are there. Which operator I have to take first? Exponential. So that's why I'll do exponential first, then braces is closing, that's why I have to complete this one. So A followed by whatever the operation followed by plus, right? This part is over. Division of this entire thing. Okay, so I cannot directly make division. First I have to take the braces. EF followed by minus, right? E minus F will become EF minus. This part is over. Now the thing is, you can observe it's something like this is something like I'll take this entire as x divided by this as y plus g, right? Now there are no braces here. If there are braces, I'll go for y plus g, but now you can see division is the first priority compared with plus. So now I have to take x division y. So that's why we need to take division now. So this part x means this entire part, right? So y means this entire part. Now division will come, and finally this g. So g followed by plus. So I think this is our answer, right? ABD cap plus like this, EF minus slash g plus. I think our option A is correct answer. So we need to do carefully. If there is a brace, then our answer will be another. Like first I have to complete this part, then this part. So then our postfix expression will be changed. Moving on to the question number 13. This is a question with respect to a graph. It is given an undirected graph where self loops are not allowed. Okay, the vertex set of G. Okay, here is given a constraint when you have to get an edge. Of course, I have given this example like there are 12 edges, like 1 to 12 means, sorry, there are 12 vertices. Okay, and 12 vertices, how it can be arranged such that it is taking I comma j is an edge. What is I comma j? So from I vertex to the j there is an edge. When it is an edge, you can see there is an edge between. Okay, this is a one vertex point. I comma j means it is a point. It's something like 1 comma 1 is a one vertex, 2 comma 2 is a vertex, 3 comma 3 it's like some vertices. So when I can write an edge, so I can write a comma b comma c comma d if there is a difference at least, sorry, at most one. There is a difference at least at most one. That means I'll take one simple example, 1 comma 1, 1 comma 2. So if I take this as a, this as b, this as d, c, d, so I can say that what is a minus c? 1 minus 1, 0, of course, less than 1 minus 2, yes, fine. I can take this as one edge. So like this, I can take 1 comma 1, 2 comma 2 also. I can take 2 comma 1, 1 comma 2 also. But I cannot take 1 comma 1 and 1 comma 3 as an edge. Why? Because 1 minus 3 which is exceeding. I cannot take 1 comma 1 and something like 5 comma 1 as an edge. Okay, one vertex, it's exceeding, right? So there are all the edges. That means indirectly I can say that like this, all the edges you have. Okay, like this. Now total number of edges you have to find it out. Okay, so but be careful while you are finding the number of edges. So it's not simply, you may think of, okay, each cell totally I'll find, I think totally 12 vertices. That's why I'll find 11 boxes, right? 1 2 3 4 5. So you'll find only 11 boxes, not 12, 11 boxes. Horizontally and vertically you may think of 11 into 11. Okay, and each will have 6. So like this it will be a wrong answer, right? You have to be careful. Why? Because there are common edges while you are finding. If you take this cell and this cell, so this will be a common one, right? So like this we need to check it out which are common one, and we have to ensure that. So that's why what I'll do here is I'll check it out. First I'll take this edge and this edge which are inside a cell, right? Which are inside a box. So two edges inside each box. So now first I'll take totally 121 into 2, so which is 242. First I'll take this one. So there is no common things. If you take like this for each one, like this for everything, like this here like this, there is no common edge you will find. Now I'll take this one, this edge, this edge, this edge, like this I'll find 12 edges, right? 12 edges, it's not 11. Why? Because you can count totally 12 into how many you will find like this. Here this is one row, like this how many rows you will find? Like this 1, 2, 3, like this only 11 only. You can observe, so 11. So totally 132, right? 132 like this vertical edges. So the remaining are horizontal like this. So like this how many I will find in a row like this? 11 I think. Sorry, 2. Yeah, 11. And like this how many here? You will find 12 here. You can say 1, 2. If the lines you can consider, 12 you can find. That's it. You can add up all these things. So totally 506 edges you will find here. So option C is our answer. You can check it out clearly how we need to consider. Coming to question number 14. So this is a question regarding the linked list concept. The address of the first node of a linked list is consisting of an integer and a pointer to the next address node is 1000. What will be the address of the second node? So linked list will have a node data part and address part, where data something like x will be there, address will be there here. So this address something like here it is giving 1000, some example. So here it is asking what is the address of this one. So in a linked list we know that the memory will be allocated dynamically. There is no sequential memory location, which is there is no guarantee, like might be in very rare case, might be, but there is no constraint, like there is no sequential memory addressing. So this might be 1000, this might be another, somewhere you will take 1286, somewhere the next sequence will take something like 4000, 423, like this it will take. Okay, so random address, so we cannot say directly this is the address, whereas in the concept of arrays we can say. So that's why the answer is here we cannot predict, right? So we cannot say it is a sequential like this, we cannot predict. So that is about the concept of linked list, where the address, of course the values are sequential, right? So if what is the next value of this address means, next value means it has to go to the address. So address, what is the address? It will be stored here 1286, right? The next here the address will be 4423. So like this, that's why we call it as the values logically sequential but not physical. Logically they are sequential, the values in a linked list, but not physical. Physically they are different memory locations which are not in sequence. Option D is the correct answer. Question about circular queue. So if in a circular queue the front is at 9, we know that front means we can delete the elements, from rear means we can insert the elements. The deletion of an element will make. So front is at 9, here F is there front, and rear is at 4, here R is there. So from this position you have to insert the element. When you insert here, it will some element, the element will go here. If you insert, the element will go here, like this it will be. But when you delete, so here 9, if I delete, the next position of front will be here itself. So the answer is A option, that is the position is 0. Moving on to the question number 16. A sort which uses binary concept such that any number is larger than all the numbers in subtree. Of course larger it is possible, somewhat smaller is also possible, which is, we know that this is heap sort. So where the concept of heap sort, which follows a concept of like tree like structure, where each element has to be inserted. There are two types of binaries you can find here. One is Max-heap, the other one is Min-heap. Where in Max-heap every element for every node, the descendant, all the nodes, all the values will be definitely less than, and for min heap all are greater than. Simply like this we can take something like 70, I'll take here as 50, here something like 40, here 20, here 10, here 30, here something like 35. So for 70 all these descendants are less than, you can see. So for 50 these descendants are less than, for 40 these descendants are less than, right? So like this it will be, this is, we call it as heap, max heap, and min heap quietly reverse, this will be greater. Okay, for root all the descendants will be greater, like this. And for each node you can see like this arrangement will be there. This is, so how this, that means sorting can be done means, if this is the arrangement, now I'll take this in an array. First I'll take the root at 70 this position. Next let us suppose I'll take the indices 0, 1, 2, 3, 4, 5, 6 like this. Anyway 7 elements are there from, so 70. Now now after deleting this is empty. Now I'll keep this 35 here, right, the last, extreme last element in this. That means the arrangement will be like this. Here it will fill, next here, next here, next here, next here, like this. So this 35 will come here. Now it will be checked out 35, 40, 35, 40, 50. Among these three, whether they are following, no, which is highest, 50. 50 will be here, 35 will be here. Now here also you need to check it out, the condition. 35 is greater than 20 and 10, yes, true. So no need of exchanges or swap. So like this, next highest is 50, will be taken here and remove here. Take this 30 here. Now again check it out, 30, 35, 40, highest is 40. 40 will come here, 30 will go here. Anyway, no descendants here. Now 40 will come here. Okay, next the element is 10. Okay, 40 will go here, 10 will come here, 10 and 35, 30. 35 is the highest, 35 will come here, 10 will come here. But you can see 10 and 20, so not following the Max-heap property, so that's why 20 will be here, 10 will be here. So like this will be taken and you will get the values here 35, here 30, here 20, here 10. So like this arrangement you can find in the concept of heap. So like this we can sort the elements, you can find here. Okay, this is the arrangement we can take for the concept of heap sort. Now the next question, which is with respect to the heap sort only, you can see here the question number 17. The minimum number of interchanges needed to convert the this array into a heap with maximum element at the root. So the condition here, maximum element at the root, means we must have to construct max heap, right? So how to construct? Okay, we'll construct the tree here, 89 at the root initially. Okay, anyway, first I'll start like this. This is a one node, this is totally 3, 3, 6, 3, 9, 13 elements. Have to take like this. So now this index 0, 1, 2, 3, 4, 5, 6, like this, 7, 8, 9, 10. So now we'll see this one. First 89, first it starts from the first empty position, that is 0. So that's why directly 89 will be taken here. Okay, next the element 19. So next position 0, a of 0 is over, a of 1, 19, and check the condition whether it follows the property of heap, max heap. Yes, 89 is greater than 19, fine. Okay, no need of any interchanges or swaps. Next 40. Okay, here now is there any interchanges? Not required. Okay, 89, of course 40 is less than, right? Now the next element 17 here, right? So next position here it will be taken and check the property. Is it less than 9, the parent? Yes, true, that is fine. 12 here, is it less than parent? 19, yes, true. Next element 2 here, and the next element 10 here. Is it less than parent? Yes, true. Next element 2, it is less than parent. Yes, if it is less than parent means here it is less than 89 also, that is a root. Okay, like this. Now the next element 5, here it is less than parent. Yes, true. Next element 7, here it is less than. Yes, true. Next 11, yes, true. Yes. Next element 6, yes, true. This is also true. We'll see. Next element 9, here is it? See, never you can check like this element only with the parent you have to check, other than that you cannot check. Like 11 with the 17 is not required. Okay, so like this. 9 with the parent, yes, true. But finally 70 with the parent 10, yes, it is not following the property, so interchange. So 10 here 70. Now 70 with the parent, not following the property, so 40 here, 70 here. 70 with the 89, yes, following the property. 70 is less than 89. Now it is fine. So how many interchanges we have done? Only 2 interchanges, right? This one swap, and here, so only 2 swaps are required. So that's why option C is the correct answer. So like this we need to swap whenever it is not following the property. Coming to the question number 18, again from the concept of heap. So this is very interesting. Suppose we are sorting an array of 7 integers using heap sort, and we have just finished some heapify. That means heapify operation, I told you, no, whenever it is constructed as heap tree, now we have to get the heap value. So how we need to get, anyway I'll explain for the previous how to get it as an array for this question, for the 17, for this question. Afterwards I'll go to that one. Yeah, here you can see after this one, first 89 will be taken, last position, that the last index, I think the index number 12, and here this place will be replaced with the last element. What is the last element? 10. Now the property of exchange has to be done. 10, 19, 70, highest is 70, 70 here, 10 here. So now 70 will be taken. So like this we need to. Now here also 10 with the property, 10, 46. So 40 is the highest, 40 will be taken here, 10 will be here. Now 10 and 9 fine, but here 12 it is there, so no. So 10 and 9 it is fine. Now again it will check with the 70 is fine, 70 will be replaced with 9. So here 70 and this 9 will be into an array, so that is fine, and 9 with the swappings. So like this it will happen, and the array will be look like this. So what is the next highest? 40, I think. So next highest will be filled, and this array will be our sorted array. Okay, similarly here it is telling some elements are there, some heapify operation is over. Okay, first thing we have to find whether it is Max-heap or Min-heap. He is not given the clarity regarding this. He told either Max-heapify or Min-heapify. The array now looks like this. After some operations, array is like this. How many heapify operations have been performed on root of heap? So till now, that means how many operations are filled. So the first thing we need to observe from the last. Anyway, we have seen the elements are filling from the last. You can see, check it out, 28, 27, 12, 10, like this. So this is, can I say it is a descending order? Whenever there is a descending order, we say that yes, it is a Max-heapify. If it is increasing order, we can say Min-heapify. Remember this point. Okay, if it is decreasing, Max-heapify. If it is increasing, Min-heapify. So now let us suppose 28, I think this is the highest. Why? Because you can see among these elements, highest will be at the last. 28 is last. 27 second highest, that is also over. That means 2 operations are over. 12, is this highest from the remaining elements? No. So that's why I can stop here. See, you have to check the property. 28, is it highest among all? Yes. Next 27, is it highest among all? I mean from the left elements? Yes. Now here 12, it is not. If let us suppose here if I get 16, I can say that yes, 16 is also swapped, like that is also sorted. So like this. So that means 1, 2, only 2 heap operations are over. So that's why largest 2 elements in the last 2 positions. Can you take large 3 elements from the last? No. Why? Because it's a 12, but there is a 1 element greater than 12. So like this we need to consider, and we can say that only 2 operations are performed till now. So that's why the answer is option B. And how this heap sort will be done, you can see here also. Swap the root with the last element that I explained. Okay, then call Heapify. So I think the root element is initially 28, so that is swapping with the last element. Anyway, irrespective of whatever it may be the last element, I think it will be some element, whatever it may be. Next highest you will get it as 27, and next highest like this it will take. Okay, so this is about how we can identify after few operations how many how many operations are performed in a Heapify. So question number 19 regarding the queue. Queue is an empty queue. I'll take an empty queue. So front and rear initially. So initially queue is empty. Add 5. Let us suppose from rear I am entering 5. Okay, now only 1 element front is at that position. Add 7 added, add 46 added. Next delete. Delete means 5 will be deleted, which is in the front. Now front will be here. The first element is 7. Next add 13. 13 will be added. Next delete, 2 times delete. So 7 will be deleted for the first time. Next 46 will be deleted for the second time. So now F will be here. Next add 10. 10 will be here. Now what will be the content of queue after these operations? Of course front is marked by F, rear is marked by R. I think the front is 13 and rear is 10, right? Okay, front is 13, right? Rear is 10. So option A. So answer option A is a correct one. How many distinct binary search trees can be constructed with 3 distinct keys? So 3 keys have taken. Let us suppose I'll take 3 keys as 10, 20, 30. So how many distinct binary search trees? So let me take the first one as 10, 20, 30. Okay, second one I'll take 20, 10 on the left, right? 30 is another arrangement. If I take 20 followed by 10, 30. So all the arrangements you can take, right? Next I'll take 30, 20, 10. Okay, I'll take one more 30, 10, then 20. This is also fine. One more I can take, right? So like 10, 30, 20, right? Like this we can take. And is there any other? Nothing. 5 I can get it. So answer is 5. But what if I ask you instead of 3, if I give n distinct keys? So there is a formula. Directly you can get the answer, right? So I'll show that formula. That is, this is a formula. So if n is a number of nodes, you have to follow 2n cn by n plus 1. Let us suppose in our case, if n equals 3, you can see 2 into 3, 6, c3, which is 20, right? By n plus 1, which is 4. So you can just give for any n value. Let us suppose if it is 5. So 5 into 2, 10 c 5 divided by 6. So like this you can consider. So this is a formula. Remember this formula. So where you how many distinct binary search trees you can construct with n number of distinct keys. Coming to the question number 21. Of course the question is related to binary tree. So here it is a function is given. Function is supposed to calculate the maximum depth or height, we call it as. So what is this height or maximum depth? The number of nodes along the largest path from root node to the down. It's simply like we know that a binary tree. Yeah, we know that binary tree consists at most 2 children for each node. Okay, it may be less or it may be 0, it may be 1 or it may be 2, but not more than that, right? You cannot get one more node here. Okay, yeah, let us suppose this node is 1, this is 2, this is 3, this is 4. Of course you can make like this. And now what is the height of this binary tree? Let us suppose, so nodes from root to the depth, maximum longest path, that means this we call it as level 0, level 1, level 2, like this. Okay, here if you take 2 levels you have right side, I mean level 0, level 1, here you have 3, so maximum is 3, that's why the height is 3. Like this we can say. Now the code is written here where a function is taken max depth, node is given. If node is equals to null, directly empty binary tree, you can say it is return 0, else it is recursively going to max depth function to the left as well as to the right. Now if which is greater, L depth or R depth, the values whichever is greater you can take, right? Return X or Y. Now you can see here what we need to find, what is this X and what is this Y. Okay, options are given here, what must be written in place of X and in place of Y. Okay, is it L depth and R depth, or L depth plus 1 or R depth plus 1 minus 1, like this we can see. Now we'll have to clearly check it out. You may initially think like X equals to L depth and Y equals to R depth. You can keep here return L depth and else return Y depth, R depth, but you can see the problem what you will get here. It's simply like L depth, what you will get here, level 0, level 1, level 2. In this way you will get 3. Here you will get the final I am talking about 2. 3 is greater than 2, that's why 3 will be taken as output. Okay, but the code execution you can see, I'll show you line by line. So struct node 1 here, first it will take the root node. It is null, no, it goes to the left part, max depth of left is node 2, and here right is node 3. Okay, and if I take 2, the node 2 here, node 2 here, what is the L depth? You have to take, anyway it is not null, so left is 4, you will take here. Okay, node of left. Now if I take 4 here, left is null, right is null, both are null. Now you can see here, anyway now I am taking this one. Why? Because the last we have taken last, right? Now it goes to the null, and now if you take the node null, if node is null, it returns 0. That means here the values finally will be, I mean at the last recursion they will be returned as zeros. Now coming back to this node, the node 4, the value here is 0, here also 0. You can see 0 is greater than 0, false, else return Y. Let us suppose if I write this option, R depth, what is the value? 0. So it goes 0 here. Now recursive, the value for 2, it is 0, here might be 0, 0 is 0, like this you will get all. At the root you will get it as 0, which is our wrong answer. Now what we need to do is, instead of taking 0, when you are returning 0, both are 0, then what you need to return is plus 1. Okay, if I make plus 1, what happens? Here it will be returned as else return Y. Let us suppose it returns plus 1. Okay, it returns plus 1. Now it goes here. Okay, now it goes here. Now it will check it out, what is there in L depth? It is 1, right? Yeah, it is 1, it returns 1, right? Now the value is 1, this part of value is 1. Now after getting this part value is 1, next it goes to the recursive of 2. For this 2, if you take the left depth, what is the left depth value? You got 1, whereas right depth, nothing is there. You will get now 0. So 1 greater than 0. Yes, 1 is a largest. Okay, so that's why return L depth plus 1. What is L depth? 1. 1 plus 1, which is 2. Now here it will return the value 2. Now again it takes L depth, of course, anyway for this also it will recursively goes and max depth of node left, right, which are null. So that's why here plus 1. Okay, now here 2, here 1. Okay, which is a greater? 2, that will be taken here, 2 plus 1, which is 3. So in order to get like this, we must take this one. Okay, this is a very most important part. If you don't write this one here, you will get the answer as 0 only, right? So that we need to check it out, and the answer is option B. Moving on to the question number 22. Of course, regarding bubble sort, we know that bubble sort, which sorts the elements always with the swapping, which is adjacent swapping, will be done, right? So something like 8 will be compared with 12. Okay, 8 is less than 12. Okay, if they are in proper order, as it is asking ascending, proper order only, 12 and 7, no, then swap them. Now here 12 will come, right? Here 7, here 12 will come, and like this you will do in general bubble sort. Okay, if you want, you can watch in my channel, clear explanation of bubble sort is there. Now the question is, how many swaps are required? For that, you don't go for like every time you have to swap, and instead of wasting that time, you just check it out for each number. Now what you need to do is, first write all the numbers, then check it out. Anyway, when you have to swap, whenever a number, per a particular number, a number comes on the right side which is less than, then only swapping is done, right? Then only swapping is done, right? So for each number, check it out, how many numbers which are less than. Okay, for example, for 8, how many are less than? 7, 5, 2 numbers are less than. Now for 12, how many less than? For 12, 7, 9, 5, 13. For 5 only, 13 is not, okay, only 3. Now for 7, how many less than? Only 5, that is one element only. For 9, how many less than? On the right side only you check it out, only 5. 31, how many? 3 less than, 3 elements are less than. For 19, both are less than. Now 5, nothing is less than. 13, anyway for last element, no other, right? Now you can simply add these numbers. So we are getting the total count as 12, that's why the answer is 12. Directly you can write it. So our answer is option B. Coming to the question number 23. What does the following function do for a given binary tree? So it is written in C language. You can see then function, which is, of course this program is with related to binary tree. It is given the fun is a function where you are taking from root. If root is null, directly you can say empty binary tree. If root of left is equals to null as well as right, both are null, that means your root, whatever you are taking here, a node, which definitely will be a leaf node, right? If both the sides are null, okay, return 0. Else, if not, return 1 plus recursively going to the left and recursively going to the right, right? Yeah. Now what is the meaning of this one? Okay, let us suppose if I take a binary tree like this. So now what will be counted? What will be counted? If I start from root, it goes to the root and it will check left and right are not null. So that's why 1 plus, it counts 1. Okay, then going to the left and again checking, going to the right and again checking. If whenever the leaf nodes are, whenever this condition is applied, that means this if condition is indirectly for leaf nodes, right? So whenever the leaf nodes are there, you are not counting. That means you are ignoring the leaf nodes and counting the remaining nodes. Can I say this is directly counting the internal nodes? Okay, so that's why you can see the option B. You are not counting the leaf nodes. Whenever the criteria comes as leaf node, you are returning 0, right? So otherwise you are counting. Okay, otherwise you are counting 1 plus, so the parent plus going to the left and going to the right. So you are counting each one. So directly you can say this is count of internal nodes. Of course, if you change here the code, that means instead of 1 plus here something, if you write this is with respect to the leaf nodes, you will get it, and this count will be done here. Okay, that will be the code which is somewhat different compared with this, where counting the leaf nodes will occur. So the option is our option B is the correct answer. Now a question related to the graph. Here an undirected graph is given. We know that depth first search. What is depth first search? Anyway, here description is given. Stated at the node A, the nodes are listed. Okay. Yeah, listed in order they are first visited. Okay. Which of the following? So here we have to know first what is depth first search string. Depth first search. So from a graph, depth first search means if I start from a node, so you have to visit or you have to check for adjacents. Okay. If let us suppose if I start with A, what are the adjacents? B, D. Only two adjacents are there, and for these two you have to select only one. Of course, that is about depth first, right? So you have not supposed to select both. Let us suppose if I select B, again check it out. What are the adjacents for B? Okay, C, E. Of course, you can write D also, but whenever D is already visited, that's why ignore. So D like this you need to write, and among these three you have to take which is any one you have to take. Okay, let us suppose if I take C, what are the adjacents? Like this you need to go until all the vertices are visited and no cycle should be there, anyway you have to visit the vertex exactly once every time. Okay, you can go there, you can visit, you cannot take again. Okay, so now among these four possibilities we have to find which are the correct ones. So we know the property like every time you can visit each vertex such that no cycle should be there. You can check it out. A to B is fine. After going to B, B to E, fine. E to F is fine. Okay. After going to F, it is asking D. Is it adjacent? When you can check it out means already if there are no adjacents, it will go backtrack, right? A to B, B to E, E to F. If there are no, then it will go backtrack to E. Might be it will take E, but there exists vertices I can connect such that no cycle you will get, right? So A to B, B to E, E to F. Either I can take F to C or F to J, but here it is given F to D. So that's why option 1 is not a correct answer for depth first search. We'll check it out. Second one, A to B, B to E, E to F, F to C. Where is F to C? Yes, I can connect. Now what are the adjacents for C? You can see B is there but already visited. E is there already visited. So that's why I'll come back to F. What is there after F? G is adjacent. Yes, I can connect. Now you can see after connecting C you are getting G. Yes, fine. So I can take G. Now G to D. Yes, is there? Right. Okay. DFS. It is following the DFS. Right. Like this. And now you can see the third one. Okay. Anyway, second option we are satisfying. Now this one we'll check it out. A to D. A to D is fine. D to G. D to G is fine. G to E is fine. No cycle. E to B. Yes, is fine. Till now no cycle. B to C. Yes, fine. No cycle. C to F. Absolutely fine. All the vertices are covered. Okay, without a cycle. Absolutely fine. Third one also. We'll check it out. Fourth one. A to D. Fine. D to B. Fine. B to C. This is C. Fine. C to G. See, C to G, is it the directed? No. And even we'll check it out. Is there no possibilities for C? No. There are possibilities. Either after C, either I can get for F or E. But it is going to G. So, which is not following the property of this DFS. So, 1 and 4 are not correct. Only 2 and 3. So, our option B is correct. Now, question number 25. What does the following function do for a given linked list? The question related to the linked list. Yeah, first node has head. Okay, so we know that in a linked list, the arrangement like head node, then you will find the nodes here like this. So the address, let us suppose this is 1000, will be connected. That means if this is 1000, if this head node is connected like this, we can take, if this is 2000 address, okay, here I can write 2000 means this is connected like this. If this is 3000, so if I write 3000 means this will be connected. If this is not last node, like this we can write, and here some data will be there, 10 20 30. Okay, head node, the node value actually, right, 1000 means this is the first node, like this. Yeah, if head is equal, we can say no elements in the linked list. Now fun one, recursively calling head of next. Head of next, what is 1000 of next? 1000 of what is the next? This is data, this is next, right? So 1000 or 2000, it is going again recursively calling, right, without, until you will go to the null, right? So it has to print then head of data. Now tell me what it prints first. Will it print 10 first or 30? Definitely it is 30. Why? Because you can see first it is recursively going till the last. Why? Because after recursively till null it is going, right? Fun one dot head next, that means starting with 1000, it is going to the 2000, next 3000 address, then null. Okay, now it is coming here. What is the value in 3000? Address 30 will be printed. Next back 2000, 20. So can I say the elements whatever you are given, this logic prints it in reverse order, right? Whatever the elements are given will be printed in reverse order. So option is where is that? Yeah, B. It's not directly, if you see directly you feel like okay, head of next every time data, so it prints all nodes in the linked list. No, it prints all the nodes but in reverse order. Option B is the correct answer. Now if I want to print all the nodes in the same order, 10 20 30, simply what you need to do, simply this printf statement here, right? That means this function should be after printing, but here function is before printing, that's why in reverse order. Coming to the question number 26. So this is related to the graph shown in figure below. There are multiple shortest paths between the vertices S and D. Because this is a source vertex, of course something like target. Which one will be reported by Dijkstra shortest path algorithm? Of course, assume that in any iteration the shortest path to your vertex is updated only when, this is a very most important, when a strictly shorter path V is discovered. Okay, yeah. So what is the shortest path from S to T? Okay, of course you can follow the Dijkstra algorithm. Okay, you just check it out, what is Dijkstra algorithm. This also I explained in my videos in design and analysis of algorithm course in my channel. You can find that playlist. And basically how you can get this one, that means Dijkstra algorithm gives the shortest path from a source to the all the remaining vertices. Okay, you can take a source, what are the shortest paths, the remaining vertices, you can get it out. Okay, let us suppose if I consider S2D direct path is 7, might be you can get another path which is the shortest, might be you can check it out, right? Yeah, like S2D, D2D, I mean S2B, B2D. So this also 3 plus 4, 7, both are same, right? So sometimes you may get the shortest paths. Okay, so that shortest paths you have to find it out. For example, S2E, I can proceed like S2A, A to C, C to E, that is 6 here. And if I go like this, S2D, D to E, 8 here, I can go like this, S2B, B to D, plus D to E. So this is 8. So shortest is this one, right? So like this we have shortest path. Okay, yeah, anyway first I'll check it out the options here first, so that which is the shortest we'll see. SDT, what is the path? S2D, D to T, 7 plus 3, 10 here. And SBDT, S2B, 3 plus 4, 7, 7 plus 3, 10 here. S2ACDT, so 4 plus 1, 5 plus 1, 6, 5 plus 3, 8 plus 3, 11 here. And SACET, 6 plus 4 10. So definitely I can remove the option C. So if there is a competition among options A, B and D, right? So we have to find. So here you cannot say like it consists on less number of vertices, so this is a shortest path. You cannot say. And this is also very important. Whenever there exists a shorter, then only you update. Okay. So we'll see that one. And anyway, I have taken here a table in order to explain this one. Initial I'll take here all the vertices. So anyway, S is a source. I won't take that one. Now initially we have to write what is S2A, S2B, S2C, all the direct paths. Okay. What is the distance of direct paths? If there is no direct path, directly keep infinity. Okay. Let us suppose S2A, direct path is there. 4, S2B, yes, 3, S2C, there is no direct path. S2A, A to C is there. So directly write infinity. S2D, yes, direct 7. S2E, no. S2F, no. S2G, no direct path. Okay, infinity. Write S2T also infinity. Okay, initially you have to write like this, then find it out what is the minimum value in this. What is the minimum value? 3. So that means S2B, what is the direct path? I mean shortest path 3. You cannot get the shortest path other than this 3 in this even when you go for any path. Okay, that you can take. S2B is over, you write here B, let it be B is over, so not required to take B again. This is empty. Next I'll take next one, like what is S2A is direct is the shortest, or S2B B to A, that means S2A via B is the direct, I mean that is the shortest that we need to find right now. Okay, that means whenever you get minimum, that has to be taken, right? Now I'll take it out. What is S2A? 4 we know, but S2B B to A, check it out. S2B is 3, 3 plus B to A, nothing is there. So 3 plus infinity, which is infinity. So infinity and 4, shortest is 4 only. Okay, like this we need to update. S2C, anyway infinity. S2B B to C, check it out. S2B 3, B to C nothing, so again infinity. S2D, so 7. S2B B to D, 3 plus 4 7, but here also 7. Okay, now no need to update, right? So check it out here. This is a condition. Whenever there exists a shorter, then only update, otherwise don't update. So S2 to D only you have to take right now. S2E via B, what is S2B is there, B to E nothing, so again infinity. S2F, S2B B to F, no. Of course S2B B to G, no, so infinity. S2B B to T, nothing. Now 4, okay, I'll take like this, otherwise you will get confused. So 4 infinity 7 like this. So minimum value is 4, right? So S2A is 4. So this is, I am following the concept of Dijkstra algorithm. So S2A is 4. So this is also over. So you cannot get the shortest compared to this, even if you go any path. S2A directly is the shortest, right? S2A is the direct is the shortest, S2B is the direct is the shortest. We got it till now. Now we have to find. So we got A, right? So now we have to check it out. A, okay, S2A, A to C, okay, S2 actual value is infinity. S2A, A to C, what is the value? 5. 5 comma infinity. 5 is the shortest. Update it. Now D, S2D is 7. S2A, A to D. S2A is 4, A to D, nothing is there direct, so infinity. So don't update, previous value as it is. Now S2E, what is S2E? Direct is infinity. S2A 4, but for A to E nothing is there, so infinity. Now S2F, okay, S2F infinity. Anyway S2A, A to F infinity, you can no need to update. And S2G again I think you won't find, okay. S2T also, okay. Now the shortest is 5, right? So these are not required. So S2C is the shortest one is 5, that is S2A, A to C is the shortest. Now C you got it. Now we'll find out for these 5. S2D. S2D is 7. What is S2C? C2D. S2C is 5, right? Direct we got it as 5, right? S2C is 5, we got it. And 5 to, of course we got the answer, that only you have to check it out. S2C is 5 comma 5 to D. C to D 3. 5 plus 3 8. So here you have 7 and now you are getting 8, right? S2C is 5 plus 3 8. So which is the shortest? 7 only, no need to update. Now S2E. S2C is 5 and C2E 1. 5 plus 1 6. Of course I can update. Previously it is infinity, now it is 6. Now S2C is 5. C2F. Is there C2F? Nothing. Infinity. And now C2G. C2G. No. Infinity. C2T infinity. Now 7 6 all infinities, shortest is 6. So this is over. That means S2E is the shortest, which is 6. Now we have to find from E. S2E. What is S2E? Now we got 6. 6 to which we require D. S2 E to D. Yes, 1. So 6 plus 1 7. Previous you have 7. See, there is no shortest, right? You got 7 only. We cannot update, right? 7 only. Here we need to write. Yeah, here you can see S2E is 6. 6 to E to F. Is there any E to F? No. Infinity. E to G. Yes. This one 2. So 2 plus 6 8. Previously infinity. I'll update to 8. Now T. E to T is there 4. So 6 plus 4 10. Right? Now 7 8 10. The minimum value is 7. So this part is not required. So S2D direct value 7. Anyway, I have to write here S2E is not updated. S2D. These are the shortest path we got it till now. S2D 7. Now these 3 we'll see. We got here as D right now. Okay. Now S2D D to F, right? So what is D to F? D to F 5. 5 plus 7 12. I can update Y because previously infinity. Now D to G. What is D to G? Nothing is there. Infinity. That's why 8 only. Previous value I can keep it. Anyway, 7 plus infinity 7 comma 8. That's why 8 is the minimum. Next D to T is there 3. 3 plus 7 10. That's previous also 10. So that's why no need to update. Previous value I can keep. Now 12 8 and 10. The minimum is 8. So G S2G is our answer 8. So how we got S2G means 8 is directly means we got it from like this S2E, that is E to G, right? Yeah, we got it. So that's why this part. Okay, S2G is also over. Next we have only 2 F and T. So we'll check it out with G, whatever we got it till now. Okay, yeah. S2G 8, right? 8 plus G to F. Is there any G to F? No. So 8 plus infinity here 12 as it is. I'll keep, yeah, T. So G to T. What is G to T? 3 is there. 3 plus 8 11. But here previously 10 is there as it is 10. Now you can see 12 10. Which is the shortest? 10 is the shortest. So how did you get this 10? From I think E only, right? So from E. So this is a path we got it. Shortest. Okay. Now anyway, if you want you can further proceed, or else we got our answer. What is the shortest from S to T? You can see we got the answer here. Even if you want you can check it out. This one finally we got here as T. And S to T to what we need to write F. What is T to F? 5. 5 plus 10 15. But here we have 12. 12 is the shortest, which you got I think from D. So this path. Now if you clearly observe, what is the path you got from S to T? So S, A, C, E, T. There is no path we got like SDT. Yes, we didn't get as per Dijkstra, as per this condition. SBDT we didn't get. Even SBDT is also we didn't get. So this part, option D is the correct answer. So like this we have to do. We can learn from this MCQ like how to proceed with the Dijkstra and how to follow when this condition is given. Question number 27. Here it is pre-order traversal is given of a binary search tree. Which one of the following is the post-order traversal? See, whenever the question is asked like find the pre-order or post-order, we need two things for a binary search tree order. One is either a pre-order or post-order, and definitely you need to have in order, right? But here only pre-order is given, but it is asking to find post-order. So how can we find it? That means we know that whenever a binary search tree is given, if I go with the in order, of a binary search tree, definitely all the elements will be in ascending order, sorted order, right? So first in order, there is no need to mention this in order here. Even if it is not mentioned, you directly take the sorted order, which will be in order. Like if I sort these elements, now this is in order and pre-order is given. Of course above shows like it's a construction of a tree. Okay, directly how we need to construct I'll explain here. So like this it is there. What you need to do first? So first you have to and we know that in a pre-order always, okay, if you see the first element in the pre-order, that definitely will be your root node, right, in the binary search tree. So that's why in a pre-order you have 30. That's why, so 30 I will write here. Okay, I'll write 30, and now I'll take where is this 30 in the in order, not here in the in order. Where is this 30? Here. Now whatever the elements left of 30 will be in the left subtree. Whatever the elements are there on the right will be in the right subtree, right? So you can see 5 elements on the left, 3 elements on the right. Okay, I'll write that 10, 15, 20, 23, 25, here 35, 39, 42. Okay, now again recursively go for this procedure. 10, 15, 20, 23, 25. Okay, these are the elements on the left, and check it out. What is the next element? 20, which is in the pre-order, which is the root of this subtree. So 20 I have to take. Okay, here I have to take 20, and you can see in order what are the left? 10, 15, right? You have 23, 25, right? Similarly here these elements are over, right, up till 25, 23 is over. Now you can see 35, 39, 42 are the elements you have, and check it out which comes first. 39. So 39 is here, and of course anyway 2 elements are there, one is on the left, one is on the right. Directly I can write it over here. But here you can see is 10, 15 is given. Which will be on the parent, which will be a child? Can I write 15 here and left as 10, or 10 is the parent and 15 on the right? Check it out here. What is there next? 10 is there. That's why 10 will be a parent. So that's why 15 will go on to the right. If 15 is a parent, 10 will go to the left according to the binary search tree. Similarly 23, 25 you can check it out. 25 comes first. That's why 25 here. So 23 is less than here, right? So like this we can have a binary search tree. Like this we need to construct. Okay, now I think you know how to go for the post order traversal of this one. Okay, what is a post order? Means first you need to visit the nodes, then parent. Okay, like 30, for a root node parents are this. Again you go recursively until the last comes. Okay, what is the last? Here null, here 15. So 15 comes first. 15, no, 2 nodes are there, here null, here 15, and then parent. Visiting nodes, then parent. So 15, 10. Of course we have only B and D options are right. We'll check it out. 15, 10. Then checking for this one. This part is over, left part, this right part. 25, there is a node. 23 has to be visited first. So 23, then parent. 25. Then this entire part is over. Okay, and then visit the parent of this 20. Anyway, our answer is over. 15, 10, 23. Yeah, this part. Option D is the correct. Anyway, we'll continue. This part is over. 20 is the left part. And right part, 39. Again, I'll go to the left part, 35. Then node 42. 2 children. Then parent, 39. And this entire part is the left part. This is the right part. And parent, 30. Okay, like this. So, answer is option D. And remember, here in pre-order, first node will be a root node in the tree, and in the post order, last node will be a root node. Okay, last node will be a root node. Like this also you can consider. Wherever in pre-order, whatever the node is there, 30 in the post order, it will come at the last. Like that also we can check it out. So our option D is the correct answer. Again, regarding binary search tree, 2 keys are given. Okay, to write an algorithm which prints all the elements between them with k1 less than or k2. So this is a question like, let us suppose if I give k1 as something like 10, k2 as 35. That means 10 and 35. What are the middle elements? What are the middle elements in this? How to find it? So if we follow the concept of inorder, definitely these elements will be in the sorted order, right? Like 10, 15, like this, whatever I explained in the previous question. Okay. Now we have to find what are the elements in between. So what are the elements actually? 15 is there, 23, 20, of course 20 first, then 23, 25, then 30, then 35. That's it, right? Of course 35 is the element which is given, that's of course 30. So how to find? It is asking, is that needs 2 extra spaces? Is that linear solution is possible? No linear solution, and solution need 1 extra space. So in general, if we consider, so if I go with the inorder concept, you can trace all the elements in linear time only. So how we need to proceed, especially if I give k1 and k2. So I'll take k1. First I'll go with the root. Is it equals to k1? Okay, then I'll check for k2 on the right side. Is that right? Why? Because k1 is the left one. Okay, like this. If I given k equals 30, no need of going to the left part, right? Always these all elements are less than. So if it is not, I'll check it out. If it is, if your root node is less than, I want to search for k1, right? Yeah, on the right side. But if your root node is greater than k1, okay, if your root node is k1, I'll go to the left part. Now 20. Is it 20 is again greater than k1 as per our question. So I'll come to the left. Whenever it is less than, I'll go to the right. Like this we have to consider. So now it is true, right? k1 we got it. Now I'll go for the inorder traversal from here till the k2 comes. Till k2 comes, I'll go for the inorder traversal of all the elements. That's it. Where I'll go to the linear solution, and there is no extra space is required. Simply traversing like this in a binary search tree, and whenever you got like this, you are going. Okay, so like this we have to answer this question. So option B is the correct answer. And you want a written explanation, you can see here. Okay, if the root recursively we need to go. If it is greater, then recursive to the left. If it is okay, then the value key is in range, print directly the value. Otherwise smaller, recursive to the right part. Like this we need to consider where complexity is an and there is no extra space is required. Big O of 1 is fine, right? So this is about our question 28. Coming to question number 29. How will you find the minimum element in a binary search tree? So what is the minimum element and what is the maximum element in a binary search tree? So extreme left node will be your minimum element, extreme right node will be the maximum element. You can observe here in our question. So what is the extreme left? 10 is the minimum element of this BST binary search tree. Of course 42. Extreme right. Okay, this is not extreme left. You can consider this is extreme left. Okay, there is no left node. Okay, if you find 5 here, that will be the minimum in this BST. Of course this will be the maximum. So here the logic is given, you can see. So A, B, C, D, which is the correct one it is asking. So it is going here always root of left is not equals to going to the left every time. Of course seems like correct. We'll check B. Again here also going to the left. Okay, it is also, and here going to the right, that's why definitely not. This is also not. We'll check it out in these two. So this is root of left is not equals to null, then finding root equals to root of left, that means it is going like this. Okay, 30, 25 going like this until null comes. Let us suppose here it is null. Okay, root of left, that means here it is null. What it is printing? Root of data. You will get 5 anyway. Find this one. Why not this one? Why not this one? You can say, while root is not equals to null, it is not root of left. Root 5 is null? No, going to this null. Now if it is null, then only it comes to printing. What is root? Null. Null dot data? Null. You are not getting, right? So I think this is a correct answer. We have to check it out clearly. Is it root of left or root? So root of left should be there here. Okay, so that's why option A is the correct answer. And of course if you want to go to the right, I think maximum value, this will be the right answer. So for our question, option A is the correct answer. Yeah. Now this is a question regarding balanced binary search tree. How would you construct balanced binary search tree? Here we can see. So anyway, in general we'll construct a binary search tree, then we will make it balanced, right, every time. Okay. Now it is asking, how would you construct AVL tree when a set of numbers are given without performing any rotations? So actually whenever it is not balanced, like we'll perform rotations like left rotation, right rotation. But the efficient way is here, like when you find, so I think here it's simply like finding the median. That means when you find the median of the set of elements, and then if you make a root, then you construct, I think it will be balanced. Why? Because median means the middle element according to the values. So like this, if you can, there will no point of getting imbalance. Like we know that in balanced the situation, this is acceptable, but not like this. This is not acceptable, right? Here 3, here 1, like this. So this, what about this one? This is acceptable, left part and right part. The thing we can say, like the height, according to that, if it is imbalance, we have to balance. But efficient way of constructing means you have to take median. So option B is the correct answer. Moving on to the question number 31. It is given as unsorted single linked list. Suppose it has representation with a head and tail pointer. 2 pointers are there, not only 1 pointer. Check it out, the question clearly. Okay, we have 2 pointers, one is head, one is tail. Given the representation, which of the following operation can be implemented in big O of 1 time? Okay, so it is simply like this, and this is a head node. Okay, here I'll write the address, here might be 2000, like this we have. Okay, yeah, here you will have some data, here you will have address, last node anyway null, here you will have the next node address, here 2000, right? Yeah, now here 4 statements are given. We have to say which given statements are true. Okay, actually the question is which of the following operations can be implemented in big O of time, one time actually. So 4 operations are given, we'll see. Insertion at the front of the linked list. That means here I want to insert something. Okay, anyway 2 pointers are there, head pointer is there, here tail pointer, so tail pointer somewhere here it is, let us suppose. Now insertion at the front of the linked list. Here I want to insert a node. I can directly take the head value, head of next will be your new, let us suppose this is 3500. So here I can directly write, and without here this link will be taken here, then remaining nodes will be unchanged without touching the remaining n-1 nodes. I think we can do in big O of 1 space. There is no need of going to all the n number of nodes, right? So only the first front I'll take, and we head pointer we can do. Insertion at the end of the linked list. So can I insert at the end? In general if I want to insert, what you will do, head pointer you have, head of next, like this you will go until you will get null. So which takes big O of n, but here tail pointer directly we have, so directly I'll go to the tail. So here I'll insert a node, right? So after inserting, let us suppose this is 4000, I'll write here 4000 and here data, and I'll insert which is also a big O of 1, and without touching these things. Deletion of the front node of the linked list. I can delete it, right? Let us suppose this is a front node, so I can directly delete, and I can keep this address here 2000 I can keep, and I can directly write which is also big O of 1 space without touching. Deletion of the last node of the linked list. So let us suppose we have tail pointer here. Let us suppose this is a last node. If I want to delete it, this must be null, right? But it is a single linked list, always goes forward, never comes back, right? It's not a double linked list, you will find something like previous, right? So how can you make this as a null? That means you have to start from head pointer, where you must find where it is the last but one node that has to be made as null, which is not possible in big O of 1 time, right? Which takes big O of n, that means 1, 2, 3. So option C is the correct answer. So these 3 can be done in big O of 1, whereas the last one. So check it out. Deletion, this you can delete, but what is the previous node? How can you get it? So there is no previous, right? If you take the logic or algorithm for linked list. So option C is the correct. Question number 32. What is the output of the following function for start point first node of the following linked list? So if I give this is start equals null return, it's empty linked list. First you are printing the data. Okay, if you clearly observe, you are printing, then again going to the same next of next. So 1 to 2, 2 to 3, that means next of next, that means 1, after that you will print 3, next of next, right? If you simply write next means next node, but next of next 3 will be printed here. Okay, next of next 5 will be printed, and also you can see previous is also printed, right? Initially after printing, first you have to print, it will print here, you are printing here, that means it goes to the 5, and next of the elements again 5 will be printed. Next the previous, anyway you have to print these things prior, right? So that will be printed 5 after printing this. Why? Because it is just recursive. So 5, 3, 1. So this is our output, and option D is the correct answer. Check it out clearly how it will go. First it will print 1, okay, then next of next 3 it will print, 3 it will go print, next 5, but next of next means after each one it has to be printed all these things in the reverse, right? Those previous ones also to be printed, right? After coming the data, what is the data? After printing 5, next of data will be printed like this. The function reverse is a single linked list. This one line missing, one line is missing here. What should be written? Simply, if you clearly observe everything, this is a node creation, and it's a reverse, it is given, printing in the reverse. So how it can be reversed? This is a logic, it is given. Okay, everything is fine. That means whatever the nodes you are giving, as I explained here, So nodes, you are printing everything, you are making this head pointer, I mean everything in reverse, but this head pointer has to go here, right? So you can see here, so while current is not equational, everything you are making. So if you clearly check it out one by one, you will come to know, okay, which reverses the linked list, but the head node you have to get it right. How to get that head node means your head reference value should be what? The last one which is previous, you can say. Okay, so this option here, you can check it out one by one, you can trace it out. So you can get the answer as option A. Coming to question number 34, this is about balanced parenthesis, where it is using the concept of stack. Okay, you are reading a character. So if the character is open brace, push onto the stack. Else if character is a close brace and stack is not empty, pop. Okay, open brace, push, close brace, pop. Okay, open brace, if still open brace, push, still open brace, push, close brace, pop. If you get close brace, pop, like this, right? Else unbalanced, right? Print balance. Which of the unbalanced sequences does the above code think balanced? You can see in the option A, 2, 3 are there. So 3 open braces, 2 close braces. 2 open braces, it is fine, but one more left. Stack is not empty. Okay, right? So that's why it shows like a balanced. Whereas option B, open brace, close brace, okay, over. Okay, close brace. Whenever it is a close brace, you can check it out. Whenever it is a close brace, now stack is empty, right? It prints unbalanced. So it is not. And here also. So you can see that means in the stack there is an extra close brace. Extra close brace, it shows it as balanced, unbalanced. But there is a extra open brace. It shows it as balanced. Remember this point according to this logic. So that's why you can check it out where the extra open braces in this, in option A only. That's why option A is the correct answer. And not only that, one more thing you have to observe in the stack. If you get an extra, I mean, if there you get close brace when the stack is empty, that means you are getting more close braces than opening braces in any instance. So you can see this D option, 1, 2, 3 open braces, 3 close braces, but you can see 1, 2, 3, 4, yeah, fifth one you can see, there you will get extra close brace. There is where stack is empty, here you can say this is balanced, but you are getting close brace before open brace. So in this case also it will check balance where it should not show, right? So that's why. Coming to the question number 35, in a complete K-ary tree, okay, if I write k equals to 2, it will become like complete binary tree. So it is, the question is not only about binary tree, it is giving k. That means in binary tree we'll have at most 2 children, right? So k, if I take k equals 3 means it will have more, I mean 3 children at most. It will be like this. The root node will have 3, and for each node also will have either 3 or 0, right? We have learned like in complete binary tree where the nodes you can find like for each node you will have like k, for each node you will have either 2 children or 0 children, similar like this. Okay, yeah, here if we consider what it is asking, every internal node has exactly k children, that we know. So number of leaves in such a tree with n internal nodes. So in general, if the question is like this, let us suppose if I have, I'll take this one first, okay, I'll take this one first, okay. So here a binary tree, I mean this is a K-ary tree where k is equals to 3 now, okay. Yeah, how many internal nodes we have? Anyway, these 3 are leaf nodes, 1 internal node and 3 leaf nodes, totally 4 nodes we have, okay. If I just increment like this, so now how many internal nodes? 1, this will become internal node, right? Now these 3 are leaves and these 2 also. So now 2 internal nodes and 5 leaf nodes, right? So now I can write it as, okay, I can write it as simply like, here of course we got 7, totally 7 nodes. So here I can write it as 1 plus n into k. Can I write where n is the internal nodes, k is the number? This one, is it a K-ary tree? So if I write like this, you can here also see one internal node, we have 1 into 3, like this we have. So like this we can take, here also you can take 1 plus n is 3, n is 2, right? 2 into 3, so total 7 we have, right? So like this we can consider. Even you can take one more example also. So now this will become internal node, 3 internal nodes, 1 plus 3 internal nodes, and each 3, so totally 10, right? You can see totally 10 nodes, 6 leaves, and 4 are 6 7 leaves and 3 are internal nodes. So now I can say that for this K-ary tree we can say that total number of nodes are nk plus 1. Total number of nodes are nk plus 1, we know, but in that how many internal nodes will be there? So we have totally n into k plus 1 or number of nodes we have. So in that n nodes are internal nodes, and if I remove these n nodes, we'll get remaining or as leaf nodes, right? So this is very simple. Like first we need to find how many total number of nodes. In that I want to subtract internal nodes. So here it is telling like n internal nodes. So we have taken according to the formula. Now if I minus the internal nodes, the remaining nodes are leaf nodes. So now can I write it as n into k minus 1 plus 1, right? Yeah, I have taken the common here and here. So this is what, and option C is the correct answer. So like this we can consider. First we need to find total number of nodes, then you have to minus it internal nodes, then you will get it as leaf nodes. If it is mentioned leaf nodes, if you want to find the internal nodes, simply you have to subtract leaf nodes. Coming to the question number 36. So here the elements are given. So these elements are inserted one by one into the given order into the Max-heap. So the property of Max-heap is, so for every subtree, not only subtree, every descendants in the next descendant levels, the elements must be lesser than the root node. If I take here, let us suppose if I take this example, 32 is should be always greater than all these elements. 30 should be always greater than all these descendants. To the next levels we have to consider, right? So which is following this? Okay, these are the arrangement, the resultant Max-heap. Which one you are thinking about? So we'll try to construct how it can be. Anyway, initially root node 32, then 15 here, and how to insert I explained in my previous questions. So next here it follows like this is the first node, second node, third node, next fourth node, fifth node, and every time Max-heap property, check it out. So 15 is less than 32, fine. 20 is less than 32, fine. Next element 30. Is that 30 is less than 15? No. Then swap. 15 here, 30 here. Now the next element 12 here. Is that 12 is less than 30? Fine. Next 25. Here first you need to insert. Is that 25 is less than 20? No. 25 here, 20 here. Next 16. 16 here initially. Is that 16 is less than 25? Yes, fine. Now this is a heap that can be constructed. So which option is correct? I think the option, you can see option A is correct, right? You can see. Yeah, again one more question on Max-heap. It is a heap where the value of each parent is greater than that. Of course, that is what I explained right now. Now which of the following is a Max-heap? Check it out, the constraint that is, so for every element all the descendant must be less than. Okay, and one more thing, it has to follow, I told you, no, it has to follow like how the elements to be inserted. Okay, so you can observe here, if you see this one, for every element it is following the heap property, but the thing is Okay, you feel that this is a correct answer, but the thing is, once you insert here, you have to come here, then here, then here, then here, then after coming to this, you have to go for one more here, right? So it should not be empty, right? It should not be empty. So here it is empty, which is not following the heap property. This is also must be checked out. Okay, so not only the descendants should be less than, so it has to follow, first thing is heap property, then only Max-heap property, right? So this is not following here, yes, all are same, and of course it is following here. You can see the here, this part 5 and 8, you can see it is violating the rule, and here also you can see 8 and 10, it is violating here also, you can see, right? So like this we need to check it out. So that's why our option B is correct answer. So for the heap property, first thing it has to first root node. Next, of course, you can take first, you need to start with I, a node. It, let us suppose if it is 0th node, the left 2 into I plus 1, right 2 into I plus 2 has to be filled. Next, for this also, if this is a node I, like this we need to check it out, right? So like this it has to be completed, then only it has to go to the next level. Okay, like this. So our option B is the correct answer. Coming to the question number 38. So in a binary Max-heap containing n numbers, the smallest element can be found in. So smallest element, where we can find smallest element in Max-heap? Definitely that will be in leaf node, right? So definitely it won't be in any internal node, definitely it will be leaf node. For any internal, definitely if it is internal node, means there is a descendant that must be less than. So that's why the answer definitely not in internal nodes, we need to find in leaf nodes. For example, here what is the smallest element? 1, so it is a leaf node, right? So how can you find the smallest element in which time? Directly can you get the smallest element? So we need to traverse from the root to the leaves, right? Always you need to check in leaves. So in a worst case, of course it is not given worst case, but actually we need to get in worst case the element can be found. You have to search, let us suppose if it is at the last position, that means you have to compare all the n elements. So that's why you can get in big of n time, like this. So the answer is option A. Yeah, one more question, that is question number 39. On binary heap of n elements, we wish to insert n more elements. So this part is very important, not necessarily one after the another. Very most important question. Okay, this you want to insert into this heap, the total time required. Okay, in general in heap or heap sort, when you want to insert the elements, even it may be Max-heap or Min-heap, you have to insert every element in log n time, and for n elements it is n into log n time. We know this one, right? So for heap sort, but the thing you observe, anyway we learned like this, but the thing you need to observe whenever I go for the heap process, while let us suppose if I want to get this one, first I will insert something like 10, then I will insert 8, immediately I'll check for the property of heap, right? I won't like I will insert one more, then I'll check the heap property, not like that, right? Every time in general, every time when I insert an element, then I'll check for the heap property. If it is, then fine, otherwise I'll go to the next element. Let us suppose if it is 16, I'll check for a heap property, I'll arrange, if not, so 16 will go here, right? If it is a binary Max-heap, right? So this process will be done in general, but the question here it is asking not necessarily one after the other. That means initially whatever the elements you have, you insert, right? So let us suppose if I have the elements 10, 15, 20, 12, 5 like this, you insert first like this. Okay, so this is asking like first you need to insert, then you have to check for the heap property. In this case, what is the time complexity it is asking. So you have to clearly check it out, this difference. In general, in my heap sort or constructing the heap, so you will follow like this. Each element you have to first insert, then check the property, then go to the next element, right? But here it is not necessary. So first you need to get, then you have to check for operations. Now what is the complexity it is asking? See here, once after inserting, instead of going from the top, anyway I'll go for the leaf nodes first. Okay, I'll start 12 and 15. Is it fine? Yes. 5 and 15. Is it fine? Yes. So like this, and I'll go up 20 or 15, 10. No. So 15 will be here. 15 and 20. No. Okay, here 20, here 15. So like this, the arrangements I have to go for it. So for this, in order to this, I can have n comparisons. So I'll write here clearly. When I go like this, what happens? So inserting all the n elements, the complexity required is inserting all the elements first, then comparison. So comparison, then swapping whenever is required. Right? Three things are important if I go like this. Okay? Inserting all, which takes big O of n in a worst case. Comparisons, let us suppose all I have to compare, yes, big O of n. Let us suppose all to be swapped, big O of n. Finally, the complexity is big O of n. Right? So like this, we need to check it out. Okay? Remember this point clearly, like n into log n, why it is in general means whenever you insert, then again checking the swapping, checking the comparisons, but not all the time. It's something like, let us suppose you have the marks with you, 10 student marks with you. So when you want to sort them, you have taken all the question, all the answer sheets, and you are making comparing. That is the question here it is given. But in general, how we'll do means, first I'll take first student, next I'll take second student marks. Let us suppose this is 10, this is 15. I have to swap if it is descending. So next I'll ask for the third student, I'll bring it. Okay, fourth student, I'll bring it. Okay, that is our general one. But here you are taking all the marks, you are taking at a time and comparing. So this is what, and in this case, we will have the complexity as big of n. So answer is option B. Yeah, question number 40. It's a very easy one. A person wants to visit some places. He started from a vertex and then visit every place connected to this vertex, and so on. What algorithm he should use? So it's something like question from a graph, where let us suppose if you start from a node, you want to visit all the vertices. All the vertices, you have to go for breadth first search. Okay, let us suppose this 1, 2, 3, 4. Okay, this is 5, this is 6. Here let us suppose 7. Here you have like this, and here you have like this. If I start from 1, I have to visit 2, 3, 7 at a time. That is breadth first search. But if you go for depth first search, you have to select any one among all these three, right? So that is what the difference we have about depth first and breadth first. For this question, the answer is option B. Coming to the question number 41. Suppose a stack is to be implemented with a linked list instead of an array. What would be the effective on the time complexity of the push and pop operations? Okay, so stack is implemented using linked list. So if you consider effectively, if you want to implement, of course, here also given assuming stack is implemented efficiently. So if you want to implement a stack using linked list, when you want to push elements, we always push the elements. That means insert the element in the linked list at the front always, right? So let us suppose if you have first element is 6, if you want to insert, you will insert 5 at the front, then it will become 5, 6, right? Similarly, like this in a stack, how it will be initially 6, next 5, 6. That means when I want to pop, it will be like 5 and 6, right? So that's why now 9 will be inserted, next 8, let us suppose. Like this linked list will be implemented. Now if you want to retrieve from the front, you can get 8 is the first, which is the first element on the top. Okay, if you pop it, that means pop operation, push operation, you can insert at the front. Whereas pop operation, same thing, like you can delete at the front. That's it. Delete, if you delete this one at the front, this will be the top element, right? So like this we need to consider. So that means if you implement stack using a linked list, always insert that push operation will be equals to inserting an element at the front of linked list, whereas pop operation is equals to deleting an element at the front of the linked list. So for these two operations, what will be the complexity it is asking? See, if I want to insert at front, if I want to delete at the front, directly I can get it, right? So I don't want to traverse any of the remaining elements. Okay, so that can be done in big of one time, even insertion and deletion also. So that's why option B is correct answer. So remember this point for stack, like insertion and deletion, that means push and pop operations are equals to, push is nothing but insertion at front, pop operation deletion at the front. Now question number 42. Yeah, this is a pseudo code that is given which uses the stack. Okay, a number is taken as input, something number. You can see here, if I consider a stack and you are pushing n percentile 2. So if you clearly observe, so n percentile 2 means like you are getting a remainder. Okay, you are dividing with 2 means something like binary and taking the next one like this. So mostly this logic is used to get that binary representation of a number, right? So that's why let us take one number, something like I'll take 13. I think binary representation is 1101, right? 84, yes. Okay. So now if I take n as 13, how you are inserting into the stack? Like this, push n percentile 2, 13 percentile 2, which is 1, you will get it. Next n by 2, 13 by 2, which is 6. 6 percentile 2, 0, you will get it. And 6 by 2, which is 3, you will get it. 3 percentile 2, 1, you will get it. And 3 by 2 is 1. And 1 percentile 2 is 1 again. Yeah, like this. And if you pop 1 by 1, you will get 1101. Now after getting the elements into the stack, what you are doing here, popping each element. So if I pop 1, next this one, this 0, 1. So you are getting the number. What is 1101, which is 30. So that means this logic is implemented for a number to convert a number into binary representation directly. So that's why the option, you can see, yes, option B is the correct one. Sometimes we feel like, okay, stack means the elements will be in reverse order, right? So we have to check it out clearly. But this reverse is required actually when you represent in binary. Yeah, which of the following sorting algorithm does not have a worst case running time of big of n square? So you can see here, I think you can see insertion sort, worst case n square, med sort, always it is n log n, right? Whatever it may be the elements. Quick sort, worst case it is n square, of course best case it is n log n, right? Bubble sort n square only, best case it is n. But even in worst case, merge sort will give n into log n, right? If you take in insertion, quick sort and bubble sort, so even in quick sort, if the elements are already in sorted order, that will give the worst case. Whereas bubble sort, if the elements are in sorted order, that gives the best case, which is n. But whereas merge sort, there is, whatever it may be, the elements that are arranged, always it goes into n into log n. Okay, so that's why our option is option B. Yeah, consider a Max-heap represented by the array, and what you need to do, consider that 35 should be inserted. So simply do this process. So 40, 30, then 20. I explained in my previous videos, previous questions, how to insert everything. Then 10 here, then 15 here, then 16 here, so then 17. Anyway, it is all following the property of Max-heap that is given already. Now I want to insert 35. will come here 35. Now check it out. 35 is less than 15. No, swap it. Now 35 with the parent 30, again swap it, which is less than. Now 35 with 40. Okay, fine, 35 is less than 40. Now the arrangement you can see 40, 35, 20, 10, 30, 16, 17, 8, 4, 35. I think the answer, sorry, 8, 4, 15. So you can see 40, 35, 20. Yeah, this one 10, 15, 10, 30 has to be there. Where it has, you can see, I think this one 40, 35, 20, 10, 30, 16, 17, 8, 4, 15. Yes. So option B is the correct answer. Yeah, one more question. Priority queue is implemented as Max-heap. So implementation of heap can be done using priority queues. Initially it has 5 elements here. The level order traversal is given. Of course, similar question, similar to the previous question. 10, 8, 5, 3, 2. If I implement 10, 8 here, 5 here, 3 here, 2 here, right? So now I want to add 2 elements. That means 1, okay, and then 7, right? So 1, if I insert, just check the property. 1 is less than 5, fine, no need of any swapping. 7, if 7 is less than 5, no, 7 will be here, 5 will be here. So now 7 with the 10, yes, that is satisfying the property, that is fine. Now you can see the arrangement 10, 8, level order traversal, you can see 10, 8, 7, 3, 2, 1, 5. 10, 8, 7, 3, 2, 1, 5. So option D is the correct answer. So like this we need to do for heaps, how to insert the elements. Coming to the question number 46. So this is a binary search tree, stores the values in the range 37 to 573. So consider the following sequence of keys. The keys are given. Now the question is, if it is unsuccessfully searched for a key is given. What is the key? 273 is given. So if it is unsuccessfully searched, which of the above sequences list nodes in the order in which we could have encountered them in the search? Okay, if you see, so somewhere, so what sort of the sequence you will get it, that is what it is asking. So now anyway you can do in a better way, like you can construct the binary search tree for each one. Okay, you can check it out, and here is a trick for you. So whenever you want to go for this one, first check it out which elements are less than this key should be increasing order, greater than should be decreasing order in the sequence. We'll check it out. If it follows, then definitely it will be encountered. Remember this part. So for 273, if I go with the first one, greater than 2, less than 273, if I check it out, 81 and 102 are there. So are they in increasing order? Yes. So increasing sequence you can find, that is fine. But what about decreasing? Greater than. So 537, 439, 285, all these are decreasing. We'll see. All these are greater than, but are they in decreasing order? You can see 537 followed by 439, okay, 285. But 376 increasing here. So that's why this is not the correct answer. Now coming to this one, less than 273, 52, 97, 121, 195, 2. All are in increasing order. Okay, but what about greater than? 2 elements should be in decreasing order. So that's why this is also not correct. We'll see this one. Less than 142, 248, one more less than is there, 270. All these 3 increasing order. What about the greater than elements? 520, 385, 386, 345, 307, decreasing. Okay, so that's why this is following the rule. Now we'll check a fourth one also. Less than 149, 270, I think. So both are in increasing sequence, that is fine. What about greater than? 550 followed by 507, 395, okay, but here increasing, you can see. So that's why this is not. So only one which is satisfying, third one. So option D is our correct answer. So like this we need to check it out. Question number 47. A binary search tree stores the values in the range 37 to 573. The four sequences are given. Which one of the following is true? It is asking. Okay, so we'll check it out. 1 to 4 are in order sequences of 3 different BSTs. So 1 to 4 it is telling. What is a property for in order? If I say in order sequence of a binary search tree, all the elements must be in increasing order, right? Sorted increasing order. If I observe, first one is not, second one yes it is fine, fourth one no. So that's why this option is not correct. Now B. 1 is a pre-order sequence of some binary search tree with 439 as the root. So 1 is a pre-order sequence. Whenever I say pre-order, the first element must be the root node, right? What is that? 81 is the root node, but it is saying 439. So that's why this option is also not correct. Option C. 2 is a in order sequence of some binary search tree where 121 is the root and 52 is the leaf. So here if you observe 2 increasing order in order sequence, fine, I can say 121 might be the root node, you can have, and 52 leaf, which is the smallest element, yes you can have. So that's why option C is the correct, and we will see option D also. 4 is a post order sequence of some binary search tree. If I say this is a post order sequence, the last element must be the root node, right? So but it here is saying 149, but here it is 270. So that's why this option is also not correct. So option C is the correct answer. Now coming to the question number 48. What is the possible number of binary trees that can be created with 3 nodes given in sequence N, M, L when traversed and post order? Here post order sequence is given with 3 nodes. We know that in post order, so first children will come, then parent will come. If I say N and M are children and L is a parent, right? If it is a post order. So how many possibilities you can get? How many binary trees? So here I have given a list. So I'll construct whenever it is a post order sequence, the last element must be the root node, right? Keep L first, and left node is N, right node is M. This is the one basic option. Next I can take L followed by M followed by N. In this case also N will come first, then M, then L. This is also fine. And I can write L, M, then N. This is also fine. So like this also N, then followed by M. This is also fine. Then L, then M here, then N here. This is also fine. And L here, M here, then N here. So like this I can have 5 options, right? Okay, for 3 nodes you will have 5 options I can get. Other than this we cannot get, right? So like this, okay, you can see here. So the answer is option C. So coming to the question number 49. What is the worst case complexity for search, insert, delete operations in a general binary search tree? So in a worst case, if I say, of course it's not given like balanced. So let us suppose if I have elements like this, all are skewed like this, then definitely whenever I want to search this element, I need to go for the entire search tree, right? So that means definitely it has to search for n elements whenever I want to, in a worst case, right? Even if I want to insert and delete also, it has to go for n in worst case. So that's why option A is correct answer. So like this, whenever we'll go for this worst case means always the tree will be skewed, or left skewed or right skewed. This is right skewed, and if I say left skewed means like this, it will be something like 40, 20. So like this. So in this case you have to go for n number of elements, you have to traverse to get the answer. So that's why option A is the correct one. So the question number 50. What would be the asymptotic time complexity to find an element in the linked list? So to find an element, so in the linked list, if I want to go for an element, anyway in worst case, if you go, you have to search for n number of elements, right? So that's why our option B is the correct one. So you can get in big of 1 when the first element itself, that means where the element which is pointed towards head. So first element, then you'll get big of 1. but in worst case you will get n. So you never go for n square, right? So that's why this is the correct answer. So option B is the correct one. Coming to the question number 51. The height of a binary tree is the maximum number of edges in any route to the leaf path. So it is the question regarding binary tree. So first I'll write like something like I'll draw a binary tree here, something like this. So the maximum number of edges in any route to the leaf path. So here asking how many maximum edges. So here height in the sense it is giving in terms of maximum number of edges. Okay, it's not about nodes. Remember this point. Let us suppose if I have one node, there are no edges, right? So that's why height is 0. Next, if I have one more node like this or like this, now I have one edge. Okay, here one edge. Okay, so which is the maximum? 1 only. So you have to check for left and right. So 1 is the height. Let us suppose here I have 1, here 1, and here of course I'll have like this. Here 2 edges, here 2, here also 2. Okay, and here it is nothing is there, that's why 0. So here it is if you go in this path, it is 1 only you have like this here. Okay, so now here it is 2. Let us suppose if I have like this. So here the edges are 3, here 2, here also 2, the maximum is 3, right? So it is with respect to the edges. That's why here we need to start the height from 0, right? Now the question is maximum number of nodes you have in a binary tree of height h is. How many nodes you will find? So for example, if it is only one node, the height h is 0. So number of nodes is 1. How you can get it? Of course it is according to the formula. We need to clearly check it out. It is 2 power h plus 1 minus 1. Why? Because we are starting from 0. Height is 0. So 2 power 0 plus 1, 1, 2 minus 1, 1. Let us suppose it is asking maximum. That's why I'll make it as perfect binary tree every time. So now 3, h is 1. So 2 power 1 plus 1 minus 1, which is 2 power 2, 4 minus 1, 3, right? So like this, that's why option C. So here the constraint, the maximum number of edges, right? So that's why you have to consider, if you consider height is 1 like this, you will get wrong answer for this one, right? So clearly you have to observe. So h, what is h? This is with respect to the edges it is given. That's why the answer is option C. It is regarding the selection sort. 5 elements, 5 numbers are given. 7, 4, 5, 10 and 8. Yeah, Prashant uses selection sort to sort this array in descending order. So it is descending order, not ascending order. In general, in selection sort, what we'll do, we'll take this one and first if it is ascending, I'll select what is the minimum element. Let us suppose if it is 4, with the first element we'll swap, right? So 4 and 7 like this. Now this is a sorted one, this is unsorted, and now what is the smallest among 4 elements? 5. 5 will be swapped with the first element in the unsorted list. So 5 will be here, 7 will be here. Okay, then 10, 8. Now till this it is 4 and 5 sorted. 7, 10, 8, which is the minimum? 7. Of course with the 7 only to swap. So sorting here over 10 and 8, 8, 10 will be like this. If it is descending, what happens? The smallest should go to the last, right? So smallest 4 should be swapping with 8. So that means 7, 8, 5, 10, 4 it will become, right? 4 here, 8 here. Now again, what is the next smallest here? 5. Okay, 5 will be swapped with this 10 like this, right? Next smallest, okay, 7 will be swapping with 7, right? So like this we need to go and we have to find. Now the question is, what will the array contain after 2 iterations? Only 2 iterations in selection sort. See, you can do like this, but the shortcut here is after 2 iterations means we can say that okay, 2 smallest elements will be at the last 2 positions. Why? Because it is descending order. If it is ascending order, 2 smallest elements will be in the first 2 positions. So now in our question, descending means you have to check it out. where the two smallest elements should be at the last, in which case 4 and 5, right? So this is not, yes, this is 4 and 5, this is fine, this is not, so that's why 4 and 5. So first you have to check it out, 2 iterations. If it is 3 iterations, check for last 3 elements if it is descending. So now if I directly see 4 and 5 here, directly I can say the answer. No need to go for every statement, simply you have to check it out for selection sort. So what are the smallest 2 elements? Here 2 iterations, that's why smallest 2 elements which should be at last 2 positions. So answer is option B. Yeah, question number 53, it is with respect to the binary search tree where post-order traversal is given. And one more thing you can remember, post-order traversal means the root node will be the last value which is in the binary search tree. It might be 20 here, 29 will be the root, but we'll see the question. Which one of the following sequence of keys can be the result of inorder traversal? So here, this question is very very easy. Why? Because if it is asking for inorder traversal, always in binary search tree, if you go for inorder traversal, that will be always in ascending order, right? Check it out in your options, which is the ascending order, which is maintaining the ascending order of the elements. You can check it out. I think you can see 9, 10, 15, 22 here also, here. Yeah. So by seeing the options, 4 options, only option A is maintaining the ascending order of all the elements, which definitely will be your in order. Okay. So which is your in order, and directly the answer you can keep option A. No need to go for, so we have to take 29 as a root and go to the left, right, everything not required. Directly the answer is option A. Yeah. Question number 54, which is with respect to the graphs. Okay, here a weighted undirected graph. Okay, so there is a direction is given and it's a weight, each edge has weight with a positive edge weight. So yes, let u comma be an edge, let us suppose u comma v an edge. Okay, vertices are given. We'll see, it is known that the shortest path from source vertex s to u has weight 53. So a source here u, now the shortest path, of course in between somewhere some vertices are there, but the shortest is 53 and shortest path from s to v has 65. Somewhere s to somewhere, let us suppose, it is my assumption, I'll take here as 65. It might be here, it might go here, or whatever on the line also, which statement is always true. Okay, yeah, it is giving with respect to the result 12. That means, let us suppose how we can analyze. See, s to u it is given, s to v it is given, it is asking for u to v. Now the question is, when the u to v value can be maximum, when the value, that is weight to u to v, will be minimum. So the answer is, if s to u on this straight line, if s to v here, definitely the distance from u to v is maximum. Why? Because here 65 plus 53, which is the maximum value. More than that you cannot get, right? So it is 118, right? So that will be the maximum distance you can get. Now it is asking, okay, maximum distance you can get it. So what is the minimum distance you can get? If s to u is here, s to v also on the same line, 65. Now what is u to v? 53, 65. Now I can minus it, right? 65 minus 3, the 53, which is 12. So that means, what is our conclusion here? The distance between u comma v will be minimum 12, maximum 118, right? If you consider like this, so that's why at least you cannot get less than 12, right? So if you see here, weight of u comma v 12, not a correct answer. U comma equals 12, only once it might be, but not always, right? It is greater than or equals to 12, yes, true. It is always greater, no, sometimes. Okay, in one case it will be equals to 12, right? So that's why it is a combination of B and D. That's why option C, it is given greater than or equals to, which is our correct answer. Option C is the correct answer. Coming to the question number 55. While inserting the elements 71, 65, 84, 69, 67 and 83 in an empty binary search tree. So in the sequence shown, the same sequence it is inserted, the element at the lowest level, we need to find it out. So we'll insert immediately 71, 65 anyway is less than to 71. So here 84 is greater than to 71. Immediately you insert 69 is less than 71, come here, it is not empty. Again check for this one, 69 is greater, go to the right. Now 67, it is less than to 71, go to the left. It is greater than to 65, go to the right. And 69 is less than 67 is less than 69, so go to the left. And now 83 is greater than 71, come here. 83 is less than 84, so the element at the lowest level is 67. Option B is our correct answer. Yeah, here it is 83, it's not 84, right? Coming to the question number 56. Which of the following is not a topological sorting of the given graph? Yeah, for a graphs you can have the concept of topological sorting. Okay, those who don't know, they can listen now. So in a topological sorting, so you can see the path, like let us suppose if I say A to B, there is a direction from A to B. That means always in the ordering, always A should come prior to B. Always A should come prior to B. See, B followed by C and E. That means whenever you want to write either C or E, before that only B should be there. So you can write BC or you can write B followed by E, but you cannot write CB or EB. Of course you can write C and E, but why? Because there is no ordering, there is no relation for C and E. Both should come after B, right? Okay, this B should come after A, like this. So anyway you can have here, you can E to F. So E should come then followed by F, like this. So here also you can say C followed by D. That means C followed by D. You cannot write DC. Okay, and one more thing, what about B and D? See, B should followed by C, C should followed by D, means you can write B followed by D. You cannot write D followed by B. Okay, and you can write D, E, both you can write anyway, or E, D, there is no relation here. So like this we have, here it is asking which is a proper topological or sorting sequence. So that is what it is asking, right? So you can observe here. So like this it is, we'll see one by one. See, A followed by B, A followed by B is fine. B followed by C, that is fine. C followed by D, that is also fine, you can see. And E, where should E should come? What is the rule for E? E should come after B. You can see E is coming after B, right? Anyway, in the sequence, okay, after B only you have E, right? So anyway, it's not immediate, it can be anywhere, but you have to get E after B only. So you are getting, okay, and F, okay, F should be after E, and of course you can see after B, okay. Anyway, this is also fine. So that's why option A is correct. One thing, okay, it is asking which is not following, okay. Yeah, this one we'll see, A followed by B, that is fine. B followed by E, that is fine. E followed by F, that is fine. And C, where should C come? What is the property for C? C should come after B. Anyway, C coming after B, C. In the subsequence you are getting D after C, right? That is also fine. If I get something DC means, then I can say it is not a topological. So now it is C followed by D, that is fine. Now this one, A, B, E, C, F, D. A followed by B, fine. B followed by E is fine. E followed by C, there is no relation, that's why not at all. C should come after B, right? So that is also fine, right? B is, after B followed by, like you are getting C. Now F, where should F come? F should come after E. So E is here, F is here, that is also fine. What about D? D should come after C, okay, D should come after C, that is also fine. C followed by D, like this you are getting, that is also fine. So C also fine. We'll see this one, E followed by B, fine. B followed by C, fine. Here I think you will get the difference. C followed by D is fine, but you can see F. I mean F should come after E, but here you can see F is coming prior to E. So that is a wrong one, right? Of course F is coming after B, right? That is also fine. But you can see always F and E, F followed by E should not be there, and E followed by F should be there here. So it's not a F and E sequence, it is E and F sequence actually, but it is not following, right? So this is what simply a topological sorting. You can see here and check it out whenever it's a like priority wise you need to check it out. Like we'll see some levels in a competition, like if you are somewhere in level 1, if you shortlisted in level 1, then only you will come to level 2, right? And level 3, like this. Okay, so in order to come to level 3 you must complete level 2, that means these two levels should come prior to this level, right? So like this topological ordering we call it as. So here option D, which is not following the topological sorting rule. Yeah, coming to question number 57. Following is a directed graph. It is given again on topological sorting only. Number of different topological orderings you will get. So I explained in the previous question, that is how many, topological sorting, what it is, and ordering. So how many are there? Simply you can see here. Where is the relation for this one? First I can write A. See, if there is a parallel you can write anywhere. If there is a sequence, that must be followed, right? So which two? These two are in serial, that's why these two B and C must come in in this manner only. D, these two can be grouped, there is no reordering. A is the first one, F is the last one, you cannot change it, right? So now A to B or A to D I can have, B to C, like this I can have. So that means I can say that A followed by BC, anyway D there is no ordering, I can write D, and then F, this is the one ordering I can write. And first A to D can I write? I can write, okay. A, D first, then BC, then F, then like this. Anyway D followed by E, I am not changing. So this is also fine, two orderings I can write. Now is there any more? Yes, you can see A followed by B followed by can I write D? Yes, I can write. There is no relation for B and D. Now I'll write C. B followed by next C. C should come after B. Yes, fine. Next I can write E. So E should come after D. Yes, it is true. F. This is a one more, right? Is there any other? I can just reverse it like C and E, there is no relation. So that's why I can write like this, A, B, D, E, C, F. This is also one more, right? A, B, D, you can see E, C, F. Okay, E should come prior to, after D. So you are getting E after B. C should come after B. Okay, you are getting. So still any more? Yes, we have. So I started with B here. I'll write with D, DB. Yes, DB, CEF, and ADB, ECF. This is also fine, right? You can see. So totally 6 I think we can get. So answer is option D. So like this we can check it out according to the direction. You cannot change A and F, right? The positions. Okay, you can check it out like internally B and C, D, B and C, D and D. These two you can rearrange. That's why 2 into B and D I can rearrange 2. Okay, sorry, 2 plus 2, and C and E I can rearrange plus 2. So the answer is option D. So like this we need to check it out for topological orderings. Coming to question number 58, somewhat tricky. So following is the undirected graph. It is asking for value of X that will maximize the number of minimum weight spanning trees. The number of minimum weight spanning trees for this value of X is, see the question you have to understand clearly first. It is not, is it asking for what is X value? Definitely not. Check out clearly. What is the X value you can keep here? You can keep here such that you will get minimum number of spanning trees. Now it is asking minimum number of spanning trees. Minimum number of spanning trees it is asking. You can clearly check it out. So the number of that will x, that is okay, the number of minimum weight spanning trees it is asking. So don't confuse here. So what might be the x value, how many minimum weight you will get, that is the question. Okay, so in order to make it flexible, I will use one of the minimum weight spanning tree concept. We have two, right, prims and Kruskal. So for my flexibility, I'll take Kruskal. Why? Because at a time I'll take, whichever is the shortest, I'll take it first, right? So in this way, if I take, let us suppose, in this way if I take, let us suppose x value is something, anyway positive values you have 1, definitely I'll take this one first. Let us suppose if I take this one, assume that this value is something greater than 3. Okay, first I want to check this constraint. First edge this one I'll take, second edge this one. Okay, third which one I'll take, let us suppose it is greater than 3, let us suppose it is 4. Okay, shall I take this one? I can take this one, I can take this one, but this part is not I cannot take. Why? Because if I take this one, cycle, right? So if I take this one, cycle it will be, so I cannot take. Now can I take this one? Yes. If I take this one, this cannot be taken. If I take this one, this cannot be taken. So that means what I'll do, first I'll take this one, I'll complete this way, and I'll come here, I'll take either this. If I take this one, this cannot be taken, right? So like this I can go, right? Now that is a one thing I can do, or this is a one way of spanning tree. Now if I take this one, I'll take this one, I'll skip this one, that means one more spanning tree. Okay, now I'll take this one, I'll take this one and I won't take this one. Okay, and I'll take this one and I won't take this one, this edge. So are you able to get this point? So like this, mostly I'll get 4 only. That means the options. Why? Because these two are common. Mostly one will be taken. Let us suppose if it is even less than 4 also, I may take this one, 1 to 2. Okay, then I have to take this one. In that case also I have options which are less than 4. I won't get more than 4, right? So anyway, one more thing we need to consider, like if you want to construct a minimum weight spanning tree of n elements, so the spanning tree must contain at most n minus 1, right? There should not be any cycle. It should contain n minus 1 edges, right? So it consists, right? All the edges must be connected. So you will have n minus 1. N is a number of vertices I'm talking about. You must have n minus 1 edges in that. Okay, so now here I can say 1 2 3 4 5. Okay, I can go at most 4 edges only. What are my options with 4 edges? Like I explained right now. Okay, once I'll take this, when I don't take this one, but here I'll take one. So like this, if I go, I'll get only maximum 4 minimum weight spanning trees. I cannot get more than that, right? So one example I'll take here. I'll connect, this is a 1 first, this is 3, then I'll take this one 4, then I'll take this one, let us suppose 4 or 5, whatever it may be. Okay, so that's it. And of course I'll take this one. Okay, this part I'll take, all the vertices are connected. Now instead of this, I'll take this one, second minimum weight spanning tree. Now instead of this, I'll take this one, I won't take this one. Okay, anyway, this cannot be taken, right? In previous also this cannot be taken. So like this, the options we have, totally I can get mostly 4 minimum weight spanning trees, not more than that. Okay. So our option is option A. Coming to the question number 59. Let G be a connected undirected graph of 100 vertices and 300 edges. Okay, the weight of a minimum weight spanning tree of G is 500. So the weight it is given, that is minimum weight spanning tree is constructed where the weight is 500. Now question is, when the weight of each edge of G is increased by 5, so then what is the minimum spanning tree becomes, weight of this. So the logic, what I explained, like when you say the property of minimum weight spanning tree. Okay, even in spanning tree definitely there should be any cycle. And one more thing we need to remember, if there are any vertices in a graph, your spanning tree definitely consists n minus 1 edges. Okay, like if let us suppose if I want to connect n vertices, if I want to connect 5 vertices, there must be 4 edges, right? So like this, if there are n vertices, n minus 1 edges you will find. Okay, n minus 1 edges you will find. Now here 100 vertices are there, definitely I'll have 99 edges, and for 99 edges each edge is increased by 5. Each edge is increased by 5, that's why the additional weight you will get is 495. Now previous weight is 500, now additional is 495. The answer is 995, option B. So this property is very important. If there are n vertices, definitely there are n minus 1 edges in the minimum weight spanning tree. Okay, even in spanning tree, in simple spanning tree also you will have n minus 1 edges. Option B is right answer. Yeah, a simple question regarding stacks and queues. Stack S1 of size is 4, S2 of size is 5. Q1 is, Q also is taken. Okay, 1 is stack. I'll write here. Yeah, 1 is Q. I'll write here. Now we know that stack you can push from the top, you can pop only from the top. So first thing you are pushing what? Push LMAB. LMAB, and remember one more point, the size of the stack is 4 only. So that's it. So you won't have this one, right? Okay, 0 to 3. Okay, push LAMB to the stack S1, and S2 is size S5. Okay, we'll see that also. So the question is clearly given that you have to push, you have to do the stack operations, these 3 and these 3 alternatively. That means first this operation, second this one, third this one, and fourth this one, like this we need to do. Now after that you have to push, this is S2, whatever you pop here or whatever you delete here, okay, those elements have to be inserted to S2. Okay, so that is the thing here it is asking. Anyway, we will do this one. Push LMAB first. So I pushed LMAB. This operation is over. Now NQ PLQS. PLQS, anyway from the rear I'm NQing, that means I'm inserting into the queue. Now pop 2 elements. Which 2 elements will be popped here? B will be, then A will be popped. B and A. So like this, B first, then A. Anyway from the top, right? Pop 2 elements. Then NQY. What is NQY? You have to NQ here Y, right? Like this. Now I NQ Y here. Then peak. What is peak? Which is what peak will be taken, which is M will be here, peak. And here DQ until front is equals to 4. So here 0, 1, 2, 3, 4. So until front is equals to 4. So front, if I delete front will be here, if I delete this front will be here, like this. So PLQS will be taken. So PLQ will be taken. Yes, stack is stack is full. Okay. Now the question is what will be the output of the popped elements of S2 until S2 is empty. So now what if I pop? If I pop, Q will come first, next L, next P, next A, next B, right? So the answer is option C. You may think of S also will be inserted, but you can see this Q size, stack size 5 only. You cannot insert one more. So that is also one more thing we need to observe. Not only push pop, you have to check it out with the size also, right? So that also you need to consider, and according to that our answer is option C. And one more thing you need to remember, if I say peak means what is the top element, that's it. It's not like you are popping or you are popping the elements. If I pop, it has to be inserted into the stack, but here only peek, that means we are not popping, we are just finding the last element. So our answer is option C. Coming to the question number 61, the chromatic number of the following graph. So this is about the question related to graph coloring. So graph coloring means you have to color the graph such that no two vertices should have the same color. Okay, first we'll see that one, afterwards we'll come to chromatic number. First we'll see, let us suppose if I give 1 here, 1 cannot be given here, here. So I can give 1 here or 1 here. Okay, let us suppose if I give 1 here, 1 cannot be given here. So like this you can give, and you can use, we mostly use like minimum number of colors. So like this, here I can give 2, here I can give 3, so here I can give 4, like this I can give. But can I use the minimum number of colors? So that minimum number I can use, that means the minimum number that I can use to color this graph. Okay, for coloring any graph, that we call it as chromatic number. Now we'll see what is the chromatic number of this graph. That means how many, that is the number of minimum colors I can use to color this graph, that we'll see now. And before going to that, I'll go for some example. Let us suppose if I take a triangle, definitely here if I color 1, here 1 should not be there, here also, here 2, here 3. Okay, and if I take square, here 1 I can give, here also 1, these two are not adjacent, here 2, here 2. So the chromatic number here is 2, here is 3. And let us suppose if I write like this, so 1 if I give, here I cannot give 1, here 2, here something 3, here 4. Okay, for any complete graph, the number of vertices equals to the chromatic number. Remember this point for any complete graph. Okay, so this is what exactly, I mean, chromatic number. Now we'll see the chromatic number for this one. So if I give 1 here, here I cannot give, here I cannot give, here. So I can give only 2 options. You can take any one if you want. So I'll take 1 here, or you can take here also 1. And now there is no option for 1 to take. Yeah, let us suppose if I take 2 here, I cannot take 2 here, here I cannot, I can take 2 here. Okay, now the option is 3, here I can take 3 here. So can you, I am using only 3 colors. Can you use less than 3? No. So my chromatic number is 3 only. So this is what we call it as chromatic number, and for our graph the answer is option B. Yeah, the question related to AVL trees which are of balanced. Which of the following is a AVL tree or following? You have to check it out. So balanced binary search trees where the balance of, I mean, height of the left and right, if you subtract, the absolute value should not exceed 1. Right? If you see here, for every subtree also. So if you see here, let us take here, let us suppose 3 nodes here, here 3, balanced. Okay, so like this you can say 3 minus 3 0. Okay, now even for the subtrees also, here 1 node, 1 child, here 0. Like this also you can take, or 2 children, here 0, right? So 2 and 1 here, so 2 minus 1 1. Like this also you can consider. This is definitely AVL tree which is balanced. Now here you can see, and for this one, if I say here 10, if I say left, how many are there? 1 child, right 0. Let us suppose if I take like this, 1 minus 0 1, this is fine. Here if I take for this node, here 2, left right is 0. So what is 2 minus 0? 2. So should not be. So that's why B is not a AVL. Now for this one C, if I take this 10, 1 minus 0 fine. If I take for 50, here 2, here 1, 2 minus 1, 1 here, that is fine. Okay, now we'll see for this one, 150, left is not there, 0 minus 1, 1, that is fine. That is absolute value. 300 and here right side 400, so that is fine. Absolute value will take 1. And for 200, left are 2. Okay, 2 is the height you have to take. Okay, you cannot take like 2 nodes are there, you cannot take. Height we are talking. 1 2. So here also 2, 2 minus 2 0, that is fine. And for 100, here 1 2 3, here 1 2 3, 3 minus 3 is 0, that is also fine. So only A and C are AVL, which are balanced binary search trees. So option B is the correct answer. So like this we need to check it out for balanced binary search trees, which are one type of AVL trees. Yeah, consider the following AVL tree. Question number 63. It is AVL tree which is given, which is a balanced. Of course it is balanced, you can check it out for each node. For 20 there are left right, fine. For 60 you can see left is 1, right is 2, which is minus 1. And for 100, 1 minus 1 0, that is also fine. Now the question is, which of the following is updated AVL tree after insertion of 70? Now first we will insert 17 binary search tree. Where 70 will come? It will check for 60. 70 is greater, comes to the right. For 100, lesser, comes to the left. For 80, lesser, comes to the left. Now tell me, is this a balanced or AVL tree? No. Why? Because you can see for 60, left is height is 1, right height is 1 2 3. 3. 1 minus 3, which is minus 2. Absolute is 2, which should not be, right? Either you can have minus 1, 0 or 1. Okay. Yeah. Now we have to balance. How to balance? There are constraints. I think you can see all the constraints. So there are 4 cases you will find, like left left, left right, right left, and right right. Okay. So here in this case, if you clearly observe, this is a case of right left. So for 60, let us suppose if this is X, so here it is not balanced, so here it is Y, here it is Z. Now you can see first, okay, first we need to make this one. So here we need to balance, we need to take this one. So 70, 180, 70. So this should be first right rotated. I said it as right left. First we need to make it as right left. So what happens here, if I take 180, 70, if I right rotate first, it will become 80 will be the root, 70 will come here, and right side it is 100, and now the right of the 100, 120 as it is. So like this you can see now it is, and previously 60 it is fine, and here it is 20. Now this is right is over. Now you have to go for the left, this part. So here 20, 60, 80. Now this is X, this is Y, this is Z. Like this you need to consider. So now if I take this one, 80 will go. If I left rotate, 80 will be the root. Left of 80 is 60. It is 20. Now here 100 will come, not 70. I'll tell you what happens to 70. So the left of 80, whatever will be the right of the root, right of 60 will come. So like this. You cannot take 70 to the right side, right? Why? Because it is less than 80. So that's why whatever is there left should come to the right of this root. So 60 is here, so right of this. Now you can see this is a AVL tree which we will get after updating 70. So which option is correct? You can see 80, 60, 100 should be there. Yeah, I think this one 20, 70, 120. Yes. Yes, option C is the correct answer. So like this, and you can learn left, 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 right, and also you can see those things. You will come to know how this can be rotated. Yeah, question number 64. If one uses straight two-way mesh sort, it's not only mesh sort, it's a two-way mesh sort. So following elements in ascending order, then the order of these elements after second pass. So how this two-way mesh sort will happen, I'll let you know. So in simple mesh sort, the array will be divided into two parts, right? In the simple mesh sort, array will be divided into two parts, okay, almost equal parts, and then again divides until the problem is small. That is one way. So in two-way mesh sort, it takes every two elements and sorts. In a pass 1, in a first pass, every two elements will be taken and sorts. Next, every 4 elements. Next, every 8 elements. Like this it will complete. So 2047 will become as it is. 158 will become 815. And 94 will become 49. 40 30 will become 30 40, 12 17 as it is. This is a pass 1. Pass 2, 4 elements. So first 4 like this and 2. So 8, 15, 20, 47 is the order for first 4, and here 4, 9, 30, 40 as it is. They are in order 12, 17. Now if I say take pass 3, let us suppose this and this will be matched, and then I think you will get like 4, 8, 15, 20, 30, 40, 47. So 1 is missing, yeah, 9 is missing. So like this it will be, then 12 and 7 will come. Now it is asking for pass 2 only. What is the answer? This is the answer, you can check it out. So 8, 15, 20, 47, 4, 9, 30, 40, 12, 17. So option B is the right answer. So question number 65, breadth first edge is started on a binary beginning of from the root vertex. Okay, this is a vertex T at a distance 4. So in a breadth first edge it's a binary. So I'll take binary tree. So anyway it is asking maximum possible value. That's why I'll take maximum possible binary tree in each. Okay, like this. So what it is asking at distance 4. So that's why I'm taking distance 4. 1, 2, 3 like this. Anyway I'm taking 3 distance. Okay, so if T is nth vertex in the BFS traversal, so T is somewhere here, vertex or node you call it as the maximum possible value of n. Okay, so how it can be taken? Let us suppose if your T is here, okay, that is nth vertex, what will be the value? What will be the maximum value, possible value? First node. If T is here, so this is the first node, 2, 3. If T is here, that means maximum values possible are 2, 3, but maximum is 3, right? Now if T is here, the maximum value is, possible values are 4, 5, 6, 7. The maximum value is 7. If T is here, so 8, 9, 10, 11, like this up to 15, right? So 8, 9, 10, 11, 12, 13, 14, 15. So the maximum possible value is 15. So if T is next at 4th level, so it is from 16 to, you will get 31, right? Why? Because you can say this is, I can directly write 2 power 2 minus 1. This is, sorry, 2 power 1 minus 1. This is 2 power 2 minus 1. This is 2 power 3 minus 1. This is 2 power 4 minus 1. This is 2 power 5 minus 1. So this is 2 power h plus 1 minus 1. What is h? Height, which is 4. So if I consider in this manner, so our answer is option B. So at each level. So if I take the next level, 5th level, 2 power, I think 5 plus 1 minus 1, which is 63. Like this we can get it. Coming to the question number 66. Here it's a graph is given, of course, in terms of adjacency matrix, where graph has vertices as starting from 0. So 0, 1, 2, 3, 4. So like this it is given. What is the minimum possible weight of a path P, vertex 1 to 2 in this graph, such that P should contain at most 3 edges? So you have to find a path. Anyway it is from 0, 1, 2, 3, 4. You have to find a path from what is 1 to 2, okay, which is a minimum path, okay, which should consist only 3 edges, at most 3 edges. That means it should be like this: 1, 2, 3. Let us suppose 3 edges means first edge anyway 1, first vertex, last vertex 2. So in between you may have 2 more. So which is from the options? You can have either 0, 3 and 4. Right? So among these 3, 2 should be here, such that you have to find the shortest path. At most you can take less also. So let us suppose if I first find what is 1 to 2, and before that, if this adjacency matrix, if I construct a graph, so the graph will be look like this. So now we'll see what can I write here. Either 0, we have option 3 or 4. Here also 0, 3 or 4. Once you will get 0 here, here you have only 2 options, right? So I think you can check it out. 3 into 2, 6 options, we can check it out. But anyway, we can minimize this one also. How to minimize? And before that, we'll see what is the direct path value 1 to 2. What is 1 to 2 direct path value? 12. Actually it is 12. Can we get minimum compared with this one? We'll see. Okay, so 1 to 2, in the path of 1 to 2, instead of going to, I can go for 1 to 0 first. 1 to 0. What is 1? I mean, why I am taking 1 to 0 first means among in the path from 1, I can see all the paths. I find the minimum as 1, right? So that's why my option, I am taking 1 to 0. So which is equals to 1. So that is a minimum value. Let me check it out like this. Okay, that is the best one I can get first. So 0. So if it is 0, I can take from 0 to, I have only 2 options, 3 and 4, right? So I can take either 3 or 4. 3 is minimum I can take. Okay, if I take 3 here, so 0 to 3, so I'll get 1. Okay, now from 3 only one option, we have directly to 2, we don't have to go to 4. Why? Because only 3 edges. So 3 to 2, what is 3 to 2? 7. So I'm getting 9. But is there any other? So let us suppose after 1 to 0 I'll get 1 here. So 0 to 3 it is 1, 0 to 4 it is 4. I'll check it out this one. Okay, instead of this one, or 0 to 4 I'll take first. What is that? 4. So now I'll take 4 to 2. What is 4 to 2? 3 here I can take. So 4 plus 3, 7 plus 1, which is 8. See, I'm getting less than the previous, right? So like this you need to check it out. I think you cannot get more than this, right? So like this we need to check it out. You may have one more option, 0 to 4. I started from 1 to 0. You can go for 1 to 3 also. I can go for 1 to 4, but I cannot. Why? Because already it is 9. So if I take next one, you will get some more distance. That's why you have to intelligently take which is the minimum, then go to the next like this. We got it as 8 here. So option B is 8. Direct distance is 12. If you go for 1 to 0, 0 to 3, 3 to 2, 9, and 1 to 0, 0 to 4, 4 to 2, 8. And one more thing you can observe, if the constraint is given as 4 edges, my answer will be option A. Why? Because you can see 1 to 0 I have 1, 0 to 3 I have 1. Now 3 to, instead of going to 2, from 3 you can see the minimum distance, and for we have to take 3 to 4 it is 2. So I'll take like this, 1 to 0 it is 1, 0 to 3 it is 1, 3 to 4 it is 2. Now I'll go for 4 to 2. What is 4 to 2? 3. So this is 7, right? So this is a minimum, but here you can see 1, 2, 4 edges I am getting, but the question is given as 3 edges. So that's why our answer is 8. Option B is the correct answer. Now coming to the question number 67. Consider a quick sort algorithm is sort the elements in ascending order using first element as pivot in general one. Then which of the following sequence will require maximum number of comparison when this algorithm is applied on it? So maximum number of comparisons, how you can get it in quicksort algorithm? That means you can intelligently check it out. So there is a property that in quicksort there is a complexity of n square which is in worst case, that is you can get if the elements are already given in sorted order, right? So you are getting worst case n square means that means more number of comparisons. When will you get more number of comparisons? Means when all the elements are in sorted order, right? So that is the worst case complexity, that is indirectly it is asking maximum number of comparisons. So when you want increasing order, if all the elements are given in increasing order, okay, when you want to decreasing order, all the elements are given in decreasing order, you will get the complexity is maximum. So maximum number of comparisons, then the complexity is maximum. So check it out in this, which is the sorted one. So I think the first one, right? So you can see any other, there is no sorting, right? So that's why option A is the correct answer. Coming to question number 68. So two statements are given. It is asking like which of the following statements are true or false, whatever. So T be a binary search tree with height 4, minimum and maximum possible nodes. So if it is height 4, we'll write here 1, 2, 3, 4 vertices, but the height is 3 here. Now height is 4. So height is 4 means how many vertices? 5 minimum. That means skewed, right? So maximum possible. So binary search tree, I'll get here 1, here, like this, right? So here. So like this, if I go, if the height is 4, that means we know that the formula 2 power 4 plus 1 minus 1, which is 31, but here it is given as 15. So the statement 1 is false. If here 31, then it will be true. So coming to second one, in a binary tree, the number of internal nodes of degree 2 means it's like 2 children is 6, and the number of internal nodes with degree 1 child is 8. So the number of leaf nodes in the binary tree is, so we know one thing like that is number of leaf nodes is equals to number of internal nodes, right? Internal nodes plus 1. But here it is, of course, with children 2 only will take. So that is given as 6 plus 1, which is 7 only. You will get internal nodes. Okay, sorry, that is leaf nodes. You will get only 7, but it is given as 15. This is also wrong. So both statements are wrong, right? So either option D is the correct one. Coming to question number 69. Suppose we are sorting an array of 8 integers using quicksort again. We have just finished the first partition. Now the thing is, after first partition in quicksort, that means your pivot element will be somewhere such that the left elements are all less than P, right elements are all greater than to this P, right? So this right elements are greater than, so right side elements are greater than P, left side elements are all less than P, right? So like this it will be. Now if you see this constraint here, sometimes it might be a first element also, but if you see this constraint, so for 7 I think you can say for 7 left elements are less than 7, right elements are all greater than 7, and not only that, there is a possibility for 9 also. For left elements 2, 5, 1, 7 all are less than to 9, right side 12, 11, 10 all are greater than. That means there is a possibility for 7 and 9. Can you check for 12? We'll check it out once. Left elements of 12 all are less than, but right side elements are not greater than, right? So there is a possibility for either 7 or 9. So the pivot could be either 7 or 9. Pivot could be 7, but this is true, right? But it is not 9. 9 can be, there is a chance, right? Pivot is not the 7, it could be 9. This is also wrong. So that is what the first one is the possibility we have, where you can have pivot is either 7 or 9. Question based on hash table. It is a T with 25 slots that stores 2000 elements. What is the load factor? It is simply a formula. Directly you can take a formula, what is load factor, which is equals to number of elements, right? Number of elements by number of slots. Simply we can take, I think the answer so which is 80. So directly you can take. So if you have 2000 elements, you can take these slots, and initially whenever they are empty you can keep it, and then you can provide the links according to that. Each element can be taken with the next linker, like that. So the load factor is measured like this. So answer is option A. Coming to the question number 71. The following numbers are inserted into empty binary search tree. So these numbers are given. What is the height of the binary search tree? So what is height? And of course here I have given how it will be when I construct, and of course once again how to construct this one we'll see. We'll start from 10, and 1 is less than 10, that's why left side, and 3 is less than 10 is greater than 1, like this, and 5 is less than 10 and greater than 1 and greater than 3. So like this, 15 is greater than 10 directly to the right, 12 is greater than 10, directly to the right. For 15, less than 12 here. 16 greater than 10, right side, greater than 15, again right side. Right, like this it will be constructed. And what we need to find, height of the binary tree, which is the maximum distance from root to the last. So that means height will be 1 2 3. So 3 is the height, and which contributes 4 nodes, right? So like this we can take where you have level, this is 0, level 1, level 2, level 3, and the height is totally, and how many height is it is taken from 0, height is 3 here. That is what it is asking, maximum distance from leaf node to the root node. So like this we can take, the answer is option C. And here we are counting the distance according to the edges. So that's what it is asking, the distance. This is the 1 is the distance. So 2, 3, like this it is. So that's why it is 3. Moving on to the question number 72. So it is the following left rotate and right rotate functions commonly used in self-adjusting binary search trees. It's like balancing binary search trees. We'll have rotations, right? So like left rotation, left right, right left, and right. So here it is given T1, T2, T3. Okay, so these are the subtrees rooted with Y. It's here, it is a Y rooted on the left side, and of course here on the right side Y. Okay, on X. Okay, which of the following is the tightest upper bound for left rotate and right rotate operation? See here the question is, this T3 is a subtree, T1 is a subtree, T2. See, whatever it may be the subtree, if you want to have a rotations here, that can be done in constant complexity, right? So where you, even if it is whatever it may be, you can have the rotations here itself, right? So that's why the complexity is big of 1. So it's not like going till the last everything. So always you can get, even anyway sometimes if you have, generally you can have rotations here itself, that's it, not more than that. So that's why constant complexity, which is option E. Coming to question number 73. Consider a situation where swap operation is very costly. Now the thing is, which of the following sorting colors should be preferred so that the number of swap operations are minimized? So here you can observe where the swap operations are costly. That means first you check it out, in which sorting technique the swap operations are very less, or in which swap operations are more. So if they are very less, then I can select that sorting only, right? So in heap might be more, selection we'll check. You see, in selection what happens, first you need to find what is the smallest, then swap, right? Let us suppose if there are 6 elements, in worst case you might get 6 swappings only, right? So you have to find the smallest and taken into the first position, next position, like this. At most not only 6, you will get only 5, right? So I think here we'll get, in selection set we'll get less number of swappings, but finding the minimum value, that is another issue. But swappings are very less here. Insertion you will find more, in case sometimes you will find more, right? So if an element is smallest and here you have 5 elements, so it has to be swapped with 5 elements, right? So next merge sort also you might have, but only in selections are you are first finding the smallest at the end. That means only in the, if it is 2 nested for loops, you are making the swapping in 1 loop only, right? Outside loop only, not inside loop. So that's why most in selections are, there is a chance of getting less number of swappings compared to the remaining sorting techniques. If you want to know clearly about selection sort or all this, I kept the videos in my YouTube channel. Clearly I explained each sorting technique with example, with program, and with execution. You can check it out, everything. Coming to question number 74. Given an array of elements, which of the following is the correct sequence of elements after inserting all the elements in a min-heap? So min-heap, what is a min-heap here? So the descendants are always greater than the element. That is, let us suppose if you take root, all the descendants should be greater than for any subtree. Okay, all the descendants should be greater than, that is min heap. And we have seen about max heap, right? Completely reverse. So here, so after inserting, let us see how the min heap will come. We'll see for these elements. First 5 I'll insert, next here 7, so 7 is greater than 5, satisfied. Next 9 here, yeah, satisfied. All the descendants of 5 are less than, right? Greater than, right? You can see. Now 1, see here 1 is greater than, is it greater than 7? No. Swap here. Now 1 with the parent, 1 with 5, no. So swap here. So here 5, here 9, here 7. Now the next element 3. 3 has to come here, but we'll see 5 and 3. Okay, 3 is less than 5, that's why swap here. So, and you can see 3 and 1, yeah, they are satisfying. 3 is greater than 1. Next 10. 10 has to come here. Anyway, it is greater than 9, that is fine. Next 8, is it greater than 9? No. Swap here. Now is it greater than 1? Yes. No need of again swapping. Now 4 has to come here, right? So next lot 4, 7, yes, 4 is not greater than, so 7 here, 4 here. 4 is greater than 3, yes, true. So now the answer is 1, 3, 8, 4, 5. Yeah, the answer is 1, 3, 8, 4, 5, 10, 9, 7. If you go with the level order, and if I see in the answer, I think nowhere you find, right? So it is asking, it is an array of elements. The correct sequence means it is, I think it is asking in an array. What is the correct sequence in min heap? Definitely it is in increasing order, right? Increasing order, whereas max heap decreasing order you might get. So that's why it is increasing order. You have to take here, what is the increasing order? Option A directly. If it is a level order traversal, I can take this one. 1, 3, 8. Like this we can consider. The descendant should be always greater than the node that we'll take. So our answer is option E. Yeah, coming to the question number 75. Following array represents a binary max heap. Which one? Max heap means, I told you, like every time the element, the descendant should be always less than the element, parent element. So we'll see which is satisfying this property. Clearly check it out. So 26, I'll check it out. 26, 13, here 17 here. So descendants less than, whenever it is not, I'll skip it. 14, yeah, it is not following. So that's why this option is not correct. So I'll check for this one. 26, 15, 14, 17, yeah, this also 15 and 17, so not satisfying. This also not. Yeah, we'll check for this one. 26, 15, 17 fine, 14, 11 fine, 9 is fine, 13 fine. Yeah, this is fine. You can see for every node 15, 14 and 11, 17, 9 and 13. You can check it out. Don't compare 15 with 9 and 13. Don't compare 17 with 14 and 11. So only to that extent, to that path only we need to check it out. For 26 you have to check all. Okay. So this is fine. Anyway, we'll check for this one also. 26, 15, 13, 14, 11. That is fine. 9 fine, but 17 no. 17 should come here, right? So this is not. So that's why our answer is option C. Coming to the question number 76. Here two sequences are given. One is X and one is Y. So these two sequences, the length of the longest common subsequence. So first we have to know what is the subsequence here. So see, there is a difference between subarray and subsequence or substring. Okay, yeah, subarray, substring are same almost. If I say BC, DC like this, so continuous, I can say it is a subarray or substring. But if I ignore in between or somewhere, of course, if I take B, D, something, B and C, something like this, B followed by. So these I can say it is a subsequence. Subsequence might not be continuous. Remember this point. Subsequence might not be continuous. You can take continuous. If you take continuous, it is subarray as well as subsequence. Okay, subsequence means might not be continuous. Here you can see CAD is a subarray subsequence. What if I say CD? Is it a subarray? No, it is a subsequence. And one more thing, you cannot say that CDB is a subsequence whereas BDC it is not. Okay, reverse is not correct, right? So you have to go forward, and you can ignore. It's up to you. You can ignore and give a sequence that we call it as subsequence. Okay, the length of the longest common subsequence in X and Y. So first we will find what are the common subsequences here and what is the length of that longest common subsequence that we need to find it out. So now we'll see here, we'll check it out. What are the common characters here? You can say C and C. Okay, I can write. Okay, then followed by, you can go always forward. So indirectly we can take like this. Can we start with B first? Let us suppose if I start with B. So B, I am checking, here it is B. So I have to do like this. Then C, I have to do like this. D, no. C, no. You cannot go back. A, no. B. Yes, that's it. So one common subsequence is B, C, B, which is 3. Can we find more than that? We'll see. Yeah, you can see for C, C, C. Next D, here A is there, and D, can I, yeah, D, D. And can I find C? Yes. Can I have B? You cannot connect like this. So B, so C, D, C, B, 4 here. So like this we need to check it out. So we got 4. Can we get 5? Check it out. So this is what we call as longest common subsequence. So you can start. This is, so B2 A and B2, it is over, C is over. Next A, if I start with A here, A, B, you cannot get more than 4, right? So if I start with D, so anyway D you got it, D, C, then B only. So that is what the conclusion here, we cannot get more than 4. So there is a logic, there is an algorithm. You can check it out. I have written a program for this also. I have explained a program. I uploaded that, which is finding length of longest common subsequence. Okay, which is there in lead code problems. I uploaded a playlist, lead code problems. So there you can check it out. Not only this, I uploaded more lead code problems with solutions. So here here the option is C. Yeah, moving on to question number 77. Suppose that we have numbers between 1 to 100, and in a binary search tree want to search for 55. So which of the following sequences cannot be in the sequence? You are searching for 55. So which of the following is not in this sequence, which is not correct when you traverse? So this is where you can check it out. Whenever you can go for each checking, like taking the first and 10, go 75. Okay, then 6, like this also you can go. But here I told you one more logic, like without writing that, check it out. For 55, whichever the elements less than 55 should be in increasing order, greater than 55 should be in decreasing order. You can see wherever it satisfies, that you have to check it out. You can see for 55, what are the elements less than 10, 43? Are they in increasing order? Yes, 10 followed by 43. Greater than elements are 75, 64, 60, 50. Are they in decreasing order? You can see 75 decreasing to 64 to 60 to 50. Yes, fine. So this will come. Check for this one. Less than elements are for 55, 12, 34. Yes, increasing order, right? And also 45. No, decreasing order, we'll check it out for greater than 50. 90, the next decreasing. 68 is decreasing. Next 62, of course, decreasing. Okay, this is fine. Here we'll check it out. This is also correct. For this one, 9 is the less than 47, 43. Now we'll check it out. We'll see 9 followed by 47 increasing, but 47 followed by 43 decreasing. It should not be right. So this is not following. No need to check for decreasing anyway. If you want to check it out. Greater than is 85 to 68 decreasing, 57 decreasing, but this is not following. That's why not correct. We'll check for D also. 79, elements which are less than 55, 14, 16, 53, right? So 14, 16 increasing, 53 increasing, okay. Greater than elements 79 to 72 decreasing, 72 to 56 decreasing. That's it, fine. This is also satisfying, one is not satisfying, C. So the answer is option C. Like this also we can check it out. Yeah, question number 78. Yeah, assume the value of every weight to be greater than 10 in a graph in which the following cases of the shortest path of directed weighted graph from two vertices u and v. We want to find the shortest path will never change. See, it's simple, like something like arithmetic question, okay? Like the values will never change means it's simply like whether the value of 10 should be added or subtracted or multiplied, like this. See, in which case it is possible. Let us suppose if I add 10 to some vertex or like this. So some vertex, like in shortest path finding, somewhere you will find one vertex, some edge or not, we don't know. So if I add, the values will change. Somewhere it will be more value, somewhere it will be less, okay? So subtract also same case. But when you multiply, it follows the same order, right? It follows the same order where even some edges are not existing. Then also the values for u and v will never change. So this part is our answer. Multiply all the values by 10. You can take a graph and check it out once. You will come to know it exactly how it will be. So you can try with addition, you can try with subtraction, you can try with multiplication also. So answer is option C. Coming to question number 79. So these elements are given initially in the empty binary search tree inserted. So now here it is given, it is inserted in the order into the initial empty binary search tree. The binary search tree uses usual ordering of course. Very simple question, it is asking what is a inorder traversal. So inorder traversal means you can construct a tree here, binary search tree like this, but without constructing also you can answer this question. How to answer means, for any binary search tree, if you go for inorder traversal, the elements all will be in increasing order, right? Check it out which option where you have all increasing order. So I think option C, you can see the elements are in increasing order. So that's why I can say that this is our inorder traversal of given elements. So directly you can say without constructing BST. So the answer is option C. Coming to question number 80. The number of ways in which the numbers 1, 2, 3, 4, 5, 6 can be inserted in a empty binary search tree such that the resulting tree has height 6, right? So the height of the tree with single node is 0, it is given for our clarity. So with height 6 means, let us suppose it might be like this. Yeah, I'll start from 7, 6, okay, it should be left. One case I am taking. Okay. So 6 means 1, 2, 3, 4, 5. So like this it should be, right? So or another case is like, anyway, whatever it may be, you have to get 6. Now one more thing you need to observe. If I take the root node as 7 or I need to take root node as 1, right? Then only I will get the height as 6. Otherwise I won't get. Why? Because in these cases only, every level I have to get only one element, right? There are given 7 elements. I need to get the height is 6. Then what is the meaning here? In every level you must have only one element. So that's why when do you get one element? Either you have to start with the largest element or you have to start with the smallest element. That's why, so either it has to start with 1, there are options for 2 up till 7 or 7 you can start. There are options for 1 to 6, right? So in these two cases only we'll get the height as 6. So here in order to for this one 2 to 7 can be rearranged in 2 power 5s. Here also 1 to 6 totally 5 arranged in 2 power 5s. So 2 power 5 which is 32 plus 32 which is 64. So 64 different binary trees you can get with the height 6. Like this also you can take one more. Can you see this is a one more, 1 followed by 7, then 6, 5, 4, 3, 2. So like this we'll get totally 64. So our answer is option C. Yeah, coming to the question number 81. It is with respect to the graphs. Consider a complete undirected graph where the vertex set is given. Okay, it is represented with the adjacency matrix. Here I can represent like this, 0, or it is starting from 0, fine. So like this, and of course here it is given. If I construct a graph according to the adjacency matrix, the graph will be like this, where 0 to 1 is 1, okay, 0 to 1 is 1, like this, okay, somewhere 1 to 4 is 9, okay, 1 to 4 is 9, okay, like this. So the graph is made like this. Entry of Wij, which is a weight, okay, these values are weights given for respect to I to j, that means vertex I to vertex j. What is the minimum possible weight of a spanning tree? So here it is asking about spanning tree in this graph such that vertex 0 is a leaf node. So there are 5 vertices, so we have 0 is a leaf node first, and we have to find what is the minimum spanning tree we need to. So here spanning tree in the sense we need to get from a graph where we have to start from a one node and we have to visit all the vertices such that your total weight or cost should be minimum, right? So anyway it is giving 0 is a leaf node. Now how to proceed for this one? Okay, so here we have anyway two methods, prims and crucibles. In simple, I think we can go for crucible where it takes a minimum edge or minimum edge with weight, okay, among all the possible weights, right? So we'll see. Anyway, we'll go with this method, like whenever it is given. So whenever vertex 0 is given, I'll start from 0 in a row. I'll check it out what is the minimum value. Okay, I'll take what is the minimum value, 0, 1, 8, 1, 4. The minimum value is 1, but which repeated 2 times. That means we have two options from 0, 0 to 1 and 0 to 3, right? So that part I'll check it out first. So anyway, I'll go for 0 to 1 first, and then what I have to do here, okay, here we need to check it out, 0 to 1, then I'll take 1. So immediately I don't want to come to the node 0, that's why I'll erase these rows, the 0th row and 0th column to make it flexible. Now starting from 1, I have to take first row. The values you can see 0, anyway 1 to 1 is we can neglect, right? And of course 0 to 0 is self loop we are neglecting. After neglecting, what is the minimum that we are taking, right? And here 1 to all the remaining, right, except this value, right, 1 to 1, okay. So what is the minimum you are getting? 4, right? So that is for the node 3, right? 1, 2, 3. So after this immediately you erase first row, first column. Now from 3rd row you check it out. Anyway 3 to 3 is 0 that we are neglecting, that self loop always neglecting. So 7 and 2, which is the minimum? 2 is the minimum, which is the node 4, right? So that will select, and 4th node we select, third, that is a node here we selected is 4. Now we'll erase this one, which node we have taken? 3rd node. Anyway this is okay, 0 to, yeah, fine, 3rd node we have taken. So that's why 3rd one like this part is erased. So we are left with only one node, 0, 1, 3, 4. I think we take 2nd node. So if you go for 2, okay, from 2, right, sorry, from 4, right? From 4, so we have only one thing, 4 to 2, which is 3, right? So like this we need to consider, and if I consider the cost, here it is 1, here 1 2 3, which is 4, and 3 to 4, 3 to 4, which is 2, and 4 to 2, which is 3. So this is 10, one option we have, and anyway we'll see this one also. So first I'll go for 0 to 3, which is 1, and the cost is, and immediately I'll erase this 0th column and 0th row. Next, third one I need to go, third row, which is 4 7 0 2. Anyway, 0 is self loop, we are neglecting. The list is 2, so which is a node 4, and immediately erase third. This is third node and third column node. Now we have taken fourth node, right? So from fourth, 9 3 is there, so 9 3 is the minimum, that is the second node. Okay, so that is 3. So fourth row is neglected, and fourth column also, and anyway 0 3 4 2, the remaining is 1, right? So for 2 to 1, what is 2 to 1? 12. But if I go in this manner, we'll get 15 plus 2, 17 18. So I think this part is correct, right? Minimum path. So we have to get minimum possible weight. So which path is right? 0 1 3 4 2, which is the weight is 10. Our option D is the correct answer. Of course you can go for Kruskal algorithm, like taking which is the minimum one, 0 to 1, then which is the next minimum. Okay, you can take 0 to 3, but the thing is, it is asking 0 is a leaf node. Okay, right? Like this we need to follow for this one. So our option is answer D. Coming to question number 82, the degree sequence of a simple graph is the sequence of the degrees of the nodes in the graph in the decreasing order. Okay, so it is the degree sequence of a particular graph is given, and here a graph is not shown, but the order is given. Which of the following sequences cannot be the degree? So here, which of the following sequences cannot be the degree sequence of any graph? Okay, so that means there are some rules when you maintain a graph. The degree sequence cannot be like, it cannot be in any manner. It has to follow the rules according to if it is not, then the graph should not exist. Let us suppose we will see among these 4 options which are not correct. Okay, which are not correct sequences for any graph. So what are the rules, how we need to follow? Okay, so we'll check it out for each one. So there is a procedure, I'll let you know the procedure. What you need to do is, whenever the degree sequences are given, of course they will give in decreasing order, that means non-increasing order. If not, you have to make it as non-increasing order. Okay, so now non-increasing means I can say decreasing, but somewhere you will get the same value. That's why I'll say non-increasing order. So what you need to do is, let us suppose I want to check for the first one. So check out what is the first element, 7. Okay, now subtract 1 for all the 7 elements, next 7 elements. So next 7 elements, listen clearly. The first node, what is the value? You check it out, 7. So decrease 1 of each element, like up to 7 elements. So how many? 1 2 3 4 5 6 7 elements are there. So I'll decrease. So anyway, after decrease I'll ignore this one. So I'll start from here. 6 will become 5, 5 will become 4, 4 will become 3, again 4 will become 3, 3 will become 2, 2 will become 1, 1 will become 0, right? So for the 7 elements I have done. Okay, this procedure has to be done sequentially, you can see, until such that you should not get any negative values. If you get negative value, there you can stop and you can say this is not the correct sequence, right? So 5 is there. So next 5 elements, 1 2 3 4 5, only these 5 elements only I have to do. Okay, so 4 will become 3, 3 will become 2, again 3 will become 2, 2 will become 1, 1 will become 0. 5 elements only I have to do, right? And this 0 is as it is. And now what is their first element? 3. Next 3 elements 1 2 3, only 3 elements you have to decrease by 1. So I'll ignore this one. 2 will become 1, 2 will become 1, then 1 will become 0, and these 2 zeros are as it is. Why? Because only 3 elements I need to subtract, right? So next element is 1. You have, I have to decrease only 1 element, so that's why this will become 0 and remaining 3 zeros as it is. So that's it, over. And now you are not getting anywhere negative value. Successfully this is completed, that's why this is okay. So this degree sequence is acceptable. Okay, we'll see the next one. So 6 is there first, that's why 6 elements 1 2 3 4 5 6. So don't decrease this one, only these 6 elements. Okay, so anyway, first I'll ignore this element. 6 will become 5, next 6 will become 5, next will become 5, 3 will become 2, 3 will become 2, 2 will become 1, and this 2 as it is. Only 6 elements I need to do. Now check it out. Anyway, this should be in decreasing order. It's not, right? So first you make it decreasing order. So 5 5 5, then 2 2, 1 2 will become 2 1, right? First I'll make it should be decreasing order every time. Okay, now apply the same procedure. 5 is there, next 5 elements. Okay, up to this, ignore this one. Okay, so 5 elements, ignore this element. 5 will become 4, 5 will become 4, 2 will become 1, 2 will become 1, 2 will become 1, and this one as it is, right? Next 4, next 4 elements 1 2 3 4. So 4 will become 3, 1 will become 0, 1 will become 0, 1 will become 0, and then 1 as it is. Okay, next what happens? 3 is there, next 3 elements. So if I ignore, this will become -1, this also -1, this also -1. See, I got -1, so that's why negative value, that's why this is not the correct sequence. So like this we can check it out for each one. So there is no possibility of maintaining like this degree sequence for a graph. Okay, so this is what we need to check it out. Similarly for 3. Okay, 7 is there initially. I'll ignore 7 and next 7 elements. All are I have to take, and I'll make decrease by 1. So 6 will become 5, 6 will become 5, 4 will become 3, 4 will become 3, 3 will become 2, 2 will become 1, 2 will become 1. Now the next 5 is there, next 5 elements only up to here. So 5 will become, this has to be ignored. 5 will become 4, 3 will become 2, 3 will become 2, 2 will become 1, and 1 will become 0. So only 5 elements. So this one as it is. Okay, and one more thing we need to check it out. It's not in decreasing order. So 4 2 2 1 1 0, right? Now this is 4 is there, 4 elements 1 2 3 4. So 2 will become 1, 2 will become 1, 1 will become 0, 1 will become 0, and this 0 as it is. Okay, next you can see next part. 1 is there, so only 1 element has to be decreased. This has to be ignored. 0 0 0 0. So no negative numbers. So that's why this is okay. So this degree sequence is fine. So we'll check for 4th one like this. Okay, so initially 8 is there. So I think you can see here there are only, you can see 3 4 8 elements, and for initially for this vertex there exists 8 edges. So which is not possible. And one more thing, here remember there are no self loops allowed, and there are no multiple edges. So that is also one more constraint here. Okay, so if that case is taken, if there are n vertices, okay, for every edge, for every vertex there must be at most n minus 1, right? At most, but not n. So if there are 8 vertices, how one vertex can have 8 edges if there is a constraint that there are no self loops and multiple edges from one vertex to the another? So that's why directly I can say this is not acceptable. Okay, so that is also one more constraint. I mean, you can check it out. So whenever there is a self loop and multiple edges are not allowed. So if I see second and fourth are not satisfying, that's why option D is our correct answer. So this is what you need to check it out. First thing, go for decreasing order, then decrease each element next E elements by this number of times. Like this you need to move, and whenever there is no decreasing order, maintain the decreasing order. Okay, finally if you don't get any negative values, only zeros, then it is fine, accepted. Otherwise if you get any negative, that is not a correct sequence. Okay, so like this we need to check it out. Yeah, coming to question number 83, an abstract data type. What is an abstract data type? Okay, so I can say like whenever I take a stack, if I say stack ADT, what is that? What is QADT? What will be represented? So which represents the operations, okay, as well as data. A particular, like if I say stack, I have only push and pop, right? Like this, or finding top, a particular operations. If I say Q, like where you will find front and rear, okay, you can DQ, I mean NQ, insert and delete, right? So DQ, like this you have to, you will find, anyway in stack you will find top. So a particular set of operations maintained, that we call it as ADT, okay, stack ADT, QADT, like this will have, right? So you can see same as abstract class, not exactly, right? A data type cannot be instantiated, we cannot say. A data type for which only operations defined on it can be used, right? Only those, if I say stack means which follows the ADT, like you can take elements only from the top, right? You can only pick the element which is there on the top. You cannot take the element which is there on the bottom directly, right? So first in, I mean last in first out, which is taken only from one end you can insert and you can delete. Whereas Q, you can insert from rear and you can only delete from front, right? So that is a particular, anyway you have a different like double-ended queue, circular queue, like this. So but they are different ADTs, that is abstract data types, which are defined. So that's why it is option C. Coming to the question number 84, a list of n strings of each of length n is sorted into lexicographic order using the merge sort algorithm. The worst case running time. So a list of n strings, okay, let it be Rohit, Rahul, like this. So Virat, taken Dhoni, okay. So like this I have taken Pujara. So like this I have taken. So I want to sort this one. Okay. The worst case running time of this computation is, what is the worst case it is asking. Anyway, for sortings, okay, even in the, if you want to use in the worst case also, I can use the complexity as n log n, where you can use merge sort algorithm, right? Merge sort even in worst case also it gives n log n. Of course, if you go for other, somewhere you are getting n square and like this. This is what can be for numbers, right? It can be for numbers or characters, okay, characters or numbers. But here this n log n to be applied for strings, right? That means inside for each string this has to be applied. That's why you may get another string complexity as n, right? So for each one, so that means you have to compare those strings. That has to be done, comparing this with this. So where again the complexity is n, right? Here n with n log n. So that's why it is n square log n, right? In general, if I take the elements, I can say even the worst case, if I want to maintain, I can go for merge sort and I can say that it's n log n. But it's not a number, it's a string. One string to the another string, if I want to compare, there will get at least n complexity. right? N number of characters to be compared, right? Not only one characters. Okay, so n number of characters, that's why it is n into n log n. So that's why it is n square log n. So answer is option B. Yeah. So question regarding prefix expression. So we have to evaluate this one. So how to evaluate this prefix expression? So I think I explained postfix expression in previous questions. So this is prefix, where in postfix what we have done, we just want to find for a operator. Okay, before that you have to find two operands, right? So here also, here in reverse, like if you find a operator, you find immediately two operands, reverse, right? So there it is operands followed by operator. Here it is operator followed by operands. You can see star followed by operator is there. Again you start. So for plus, okay, for star there is no operand here. So for plus only one operand is there. Okay, two operands are there, then I can calculate. So one operand, so again plus. So 3 is there. This is exponential operator, again operator. So here 3, again now operator. See now, for this operator you have two operands followed. So that has to be done first, right? So plus 3, 3. This has to be done, which is equals to 6, right? So I'll write here 6. This 3 is as it is. And here 3, right? This part is completed. This 3 and this gap, this 3 plus and again 3 plus star. Now again check it out here. After completion of this, you can see from here again the same thing. Here you can see exponential 3 comma 6. So it is 3 power 6. It's not 6 power 3. So which is 3 power 6, which is of course again 3 cube into 27 into 27, which is 729, right? 729, here 3. Here also 3, here plus, here 3 plus star. So here you can see, I think here you can see star plus 3. So now here plus followed by two operands. 3 into 720, 3 plus 729. So this will become what? 732, right? 732, here 3, this part, and plus 3 into, right? So plus 3 and 732, which will become 735, this part, and here 3, here into. So now multiply 735 into 3, so which is equals to 2205. So the answer is option C. So remember this point, how we can go for prefix evaluation. Like we need to check from the left. Every time you have to check it out. Whenever there is an operator, immediately check it out whether there are two operands. If not, continue like this. So whenever there are two operands, you evaluate and continue this one. So like this we need to do for prefix evaluation. Our answer is option C. Coming to the question number 86. We are running the Prim's algorithm for the given graph to find the minimum spanning tree starting at node 1. Okay, so here Prim's algorithm, which is used to find the minimum cost spanning tree from a given graph. Here it is given, ignore the direction. So here the directions is given in graph, that has to be ignored. So I am ignoring all this. That means what? Here there is an edge 2 to 5 as well as 5 to 2 with the same cost. 1 to 2 and 2 to 1 is 11, like this. So 5 to 1 and 1 to 5 with 9, like this we have everything. Okay, yeah. Prim's algorithm first adds a node 1. It is asking to start from node 1 and to minimum spanning tree, the total cost of the solution. So what happens in Prim's algorithm? It's like we need to start from a vertex and you have to check for all adjacents. So adjacents of 1 is 1 to 2 is there, 1 to 3, 1 to 4, okay, 1 to 5, all are there. Among all, 1 to 2, 1 to 3, 1 to 4, among all we have to select which is the minimum. So here which is the minimum? I think 1 to 2 is 11, 1 to 3 6, 1 to 4 is 13, and 1 to 5 9. So the minimum is 1 to 3, which is 6, right? So 6, and the path is 1 2 3 first. And one more thing, you have to visit all the vertices and such that no cycle should be there for Prim's algorithm. So now from 3 you have to check it out. Now you cannot select random edge. From 3 only, what are the adjacencies of 3? You can see 3 to 1 already visited, we are not supposed to take. 3 to 2 which is with the 2, 3 to 4 which is with the 5, 3 to 5 not there, direct one. So between these two the minimum is 3 to 2. So I'll go for 3 to 2 and 2 from 2. Okay, 2 to 1 is there, already visited. 2 to 3 visited. 2 to 4 not visited, right? 2 to 4 and 2 to 5. 2 to 4 is 3, 2 to 5 is 8, which is the minimum 3. So the cost is 3. And finally from 4 to only 5 is there, yes, directly we have, and you can connect, and there is no cycle you can connect, which is the 23. So the cost is 23, and you can add all those things. 34 is my answer. So like this, if you go for Prim's algorithm, so answer is 34, which is option B. Yeah, coming to question number 87. So now we are running Kruskal algorithm for the given graph. So the graph is given, and again ignore the directions. So the question here it is asking is what is the third edge? Okay, what is the procedure if you go for Kruskal algorithm? Like in Kruskal we can select an edge, any edge which is with the minimum cost first. So it's not going with the adjacency like we have done in Prim's algorithm. So here you can select. So that's why we have to maintain the edges according to the cost. So first I'll write the minimum cost one is 2, next is 3, next is 5, next is 6, and like this. I think next is 8, next one is 9, next 11, 30, 9, 23. So first I'll take the edge with the cost 2. So what is that? 3 to 2 is the edge with the cost. I'll select first. Okay, so first edge is 3 to 2, and next I have to select 3, the cost, that is 2 to 4. So next edge is 2 to 4, I can select. So next I can select 5. But if you select 5, what happens? There is a cycle, 3 to 2, 2 to 4, 4 to 5. So this cannot be selected, right? So next one 6, so which is 1, 2, 3. Now the third edge, what is the third edge? First, second, third edge is 1, 3. Option C. It's not 3 to 4, it is 1, 3 is it. So we have to follow that rule of not getting a cycle in a tree, resultant tree. Coming to question number 88, we are running Dijkstra algorithm for the given graph for the finding the shortest path from source node 1. So Dijkstra algorithm which finds the shortest path from one vertex to the every remaining vertex. So anyway here it is given the source vertex is 1. Have to find what is the shortest from 1 to 2, 1 to 3, 1 to 4, 1 to 5, right? So here we have to remember the directions. Like there is no path from 1 to 2 directly, there is 2 to 1. Okay, so first adds a node 1 to the partial solutions. You have to find what are the next 2 nodes every time. How we can proceed, we can see. So first we have to state from 1. I'll write here what is 1 to 2 direct, 1 to 3, 1 to 4, 1 to 5 direct path. If not, write infinity. 1 to 2 no, infinity. 1 to 3 yes, 6, 1 to 4 13, 1 to 5 no, infinity. There is 5 to 1, right? So among this which is the minimum? 6. That means the shortest path from 1 to 3 is 6. Okay, you cannot get less than this one. So this part is over. First vertex is, first node is, you got it as 3, and next one. So from 3 we need to select now. So from 3 you can select the edges. What are the 3 to 2 we have, which is for the remaining you select 3 to 2 which is 2, 3 to 4 which is 5, right? And anyway no other. So 3 to 2, 3 to 4, and anyway 1 already which is a source we cannot take. So 3 to 5 which is not there, so infinity, right? Like so among these 3 which is, first we need to take this one path among, we know that 1 2 3 1 2 3, right? So which is the minimum first? 2, 5, infinity. The minimum is 2. So the total cost is 6 plus 3 to 2 is 2, which is 8. So the cost from 1 to 2 is 8. So like this, second node you got it as 2. So 3 comma 2 is our answer, right? Second and third node, next to 2 nodes. And of course you can continue for the remaining also. So like 1 to 2 I'll write here, 1 up to 2, which is 8, and remaining 2 required are one is 2 to 4, other one is 2 to 5. 3 is already over. So what is 2 to 4? Is that direct? No. Infinity. 2 to 5, yes, that is 8. So here 1 to 2 is 8 plus 8, which is 16. Here infinity, right? 8 plus infinity, infinity. So infinity 16, next node you got is 5, which is 16, and finally you will get for 4 anyway. 5 to 4 is there, you have to check it out. Yes, 23. So 23 plus 16, which is 39. So our answer, actually the first 2 nodes it is asking 3 and 2. So our answer is option A. So coming to question number 89. We are running Warshall's algorithm for the given graph to find the transitive closure. Just want to give the idea for Warshall's algorithm. So which uses for transitive closure relations in a graph. So the main difference if you go for Floyd-Warshall and Warshall algorithm is like in Floyd-Warshall you will take the weights for each edge, but whereas in Warshall algorithm you will take only whether there exists a path or not. According to that you will take which is a Boolean matrix. Okay, I'll let you know, like if I write r power 0, okay, r power 0 means which is initial adjacency matrix, like 1 2 3 4 5. So anyway 1 2 1 0 self, 1 to 2 if there exists an edge you have to give it as 1, otherwise 0. Okay, 1 to 2 no, right? So 2 to 1 is there. So 1 to 3 yes, 1 to 4 yes, 1 to 5 no, 2 to 1 yes, 2 to 2 self, 2 to 3 no, 2 to 4 no, 2 to 5 yes, 3 to 0, 3 to 1 no, 3 to 2 yes, 3 to 3 self, 3 to 4 yes, 3 to 5 no, 4 to 1, 4 to 1 no, 4 to 2 yes, 4 to 3 no, 4 to 4 self, 4 to 5 no, 5 to 1 no, 5 to 1 yes, 5 to 2 no, 5 to 3 no, 5 to 4 yes, 5 to 5 self. Right, like this we have to consider initially. Now the formula for finding r power, the transitive closure, which can be given as r power k of I comma j. So iterations you have to do where k is from how many vertices are there, those many times you have to do actually. So which is you have to find r power k minus 1 I comma j, or operation r power k minus 1 I comma k plus r power k minus 1 k comma j. So that part you need to consider, either there is this via k, whether there is a path exists or direct path. If anywhere you will get 1, the answer is 1. If both are 0 means there is no path, right? So according to that we will find what is r power 1, that is what it is asking, right? So r power 1, 1 2 3 5. Anyway these self loops won't change, and if you go for r power 1, first row first column won't change, r power 2 second row second column won't change. So that's why I am writing as it is 0 0 1 1 0 1 0 0 1. Okay, now what is r power 1? Okay, I'll write here r power 1 2 comma 3, right? So 2 comma 1 is over, 2 comma 2 is over, 2 comma 3. So which is r power 1 2 comma 3 direct? Is there an edge? No. So okay, 0 or via 1, 2 to 1 1 to 3, you check it out. What is 2 to 1? 1, and 1 to 3 1, 1 or 1 1. So 0 or 1, I mean, which you can take a positive value. So here you must have and, right, both. So plus means and you must have. That means both paths should be there, then only I can say there is a path. So 1, here 0, here 1 and 1. So that must be there. So here it is 1. So why? Because there is a path from 2 via 1. So 2 to 3 there is a path from via 1. Next 2 to 4 you can see. 2 to 1, 1 to 4. Yes, you have. So that you can check it out. 2 to 4. Is there direct? No. But 2 to 1, is there 1? You can see 1 to 4 also. So that's why this is also 1. Now 2 to 5. 2 to 1. 1 to 5 is there? No. So that's why 2 to 5 there is no path here till now. Via 1 I am just checking. And then 3 you can see. 3 to 2 via 1. Anyway there is 3 to 2 already is there. So directly keep it. Okay, no need to check. 3 to 4 you need to check it out. 3 to 4. 3 to 4 what is the value? 1. Directly you can keep it. 3 to 5 0 is there. That's why I'll check it out. 3 to 1 1 to 5. 3 to 1 no. So that's why definitely it won't be there. So that's why 0 as it is. 4 to 1 is over. 4 to 2. 4 to 2 via 1. Anyway already it is there. So directly keep it 1. No changes will happen. 4 to 3 via 1. 4 to 1 is not there. So that's why 0 here. 4 to 5 you can check it out. What is 4 to 5? 0 is there. So I'll check it out with 1. 4 to 1 is not there. That's why 0. Next 5. 5 to 2. What is 5 to 2? Not an edge. I'll check with 1. 5 to 1 is there. 1 to 2. No. So that's why 0. 5 to 1, 1 to 3. I'll check it out next. 5 to 1 is there. 1 to 3 is there. So 5 to 3 will be changed to 1. 5 to 1, 1 to 4. Yes, we have. Anyway 5 to 4 is also there. 5 to 5 self. So like this we need to check it out. Anyway we made one more 0 here. So 0 here. So like this we need to check it out for Warshall algorithm. Anyway Floyd Warshall or Floyd algorithm, if you take, what happens? Same thing, but here the formula will be changed to finding the minimum value. We'll take the weights and finding the minimum of direct edge or via this K. So this is R power 1. R power 2 means via the path 2. This has to be updated. Coming to question number 90. The contents of array, it is given, becomes after one pass of Horace partition is applied. What it becomes? Like this is an array it is given. Now what is this Horace partition? It's simply given for quick sort. For quick sort, this is a one method used for to partition. Anyway in quick sort we will select a pivot element, according that we will apply, right? So this is Horace method, which it will take always the first element as a pivot element. And it proceeds regarding the quicksort. I explained about quicksort everything. Even you can watch in my video lectures also. I explained about quicksort. And Horace partitioning means always it takes the first element as a pivot. Now if 6 is a pivot element, okay, after one pass what will be the array looks like? Okay, see, of course you can check it out according to the quicksort program, like taking this pivot, this value, whether it is less than this one, then continue, otherwise stop, and taking the last value. This is I, this is J. So if this value is greater than this, fine, continue. Like this we have to do, and whenever there is a constraint not satisfied, then you have to swap A of I and A of J, right? So that part has to be done, but here clearly check it out in the options. If P is a pivot element, check it out, all the left of this pivot element are less than, all the right are greater than this, then no need to go for this. If it is given as a multiple choice question, check it out here. Well, here it is 6, all the left are less than, no, 7 is greater than, this is not. Here you can see 6 less than, yes, all are greater than, right side of 6, of course this is fine. Let me check it out, one more is there, then I have to find, right? So here 6 less than, no, 7 is there, and here 6 less than all, no. So that's why I have only one option, that's why no need to find, directly I can say option B is the correct answer. If I have more than one like this, okay, where satisfying left of 6 are less than right of 6 are, then I'll check it out. I'll go for the procedure of 4s partitioning problem. So our answer is option B. Thank you for watching this series of video lectures on data structures MCQs. So hopefully in future I'll make more videos. Please comment in the comment section regarding this multiple choice questions, and also you can watch this one, all sorting techniques I applied in another video. I'll give in the description. So with neat explanation and different complexity analysis of these sorting techniques, you can find those videos as all sorting techniques with clear explanation. And also this one same like 100 multiple choice questions which are very most important in C language. I made it. This also you can watch in my channel. I'll give the link in description. So if you want any sort of the questions, anything, you can please comment in the comment section. So thank you very much.